Congratulations. How are you? Good.
Hard, right? You're seeing old friends, you know, you get into chats. But we'll have lots of opportunities. All right, so 11:02. Let the fest begin. Are you fired up? I am really fired up. I noticed this morning as I was getting ready, I suddenly realized I'm singing my song about Spiro. It's not happening, it just keeps happening. I couldn't believe it. Yeah. So, no, you don't want that. You don't want that. Yeah, so we have a great turnout. There are 62 more people as well, I think, will be coming in. Great turnout, and that's a real testament to the affection and admiration that we have for you, Spiro. So, many other people wanted to come. They were planning it, actually, but then because of various obligations, some of which happened last minute, they weren't able to. We have some special guests. We have Spiro's family. They're there in the back. His wife Mary, his son Brandon and Brian. I know a lot of you know Mary because they're great about inviting people to Brian, but take the opportunity over these 2 days. Next to Mary is Barbara Moore, Ron's wife. Barbara and Ron are dear friends. So it's really nice that we have everyone here for this big celebration. Now we have a great science program, and of course, because Spiro is all about the science. In fact, when I talked to him about having this, he said, well, yeah, we can do it, but science has to be front and center. We'll have opportunities during the banquet tonight for some hosting and roasting, but today is mostly about science. Why didn't people get here? 15, really? Oh, excellent. Well, thank you for joining us remotely. We wish you could be here in person. What? It's not on? Too loud? What's happening? Higher. Isn't it blasting the room now? Oh, all right. Plus, you like exactly. This is what you want, don't you? I know. All right, so we have a really nice science program, but we didn't want the schedule to be too rushed. We wanted to have time for discussion and for poster viewing. So we have half-hour breaks in the morning, hour-long breaks in the afternoon, and an hour and a half for lunch. Now, there's coffee out there all the time, so feel free just to go out whenever you want and grab a coffee. Lunch is going to be buffet style. It'll be set up out there, so just you grab the food and then sit at one of the tables out in the atrium or even outside. The weather's really nice outside. There are tables out there. Tonight we have the banquet that's right next door in this room over here. Of course, we're going to have a Greek menu. And we're going to have Greek music. That's courtesy of Joel Darlene. There's Joel over there. He has a playlist. He got some help from Spiros Paterakis and also Leah Samara, so that should be very nice. What else? What's on my list here? Let's see. Oh, well, there will be vegetarian options, and we have a couple of vegans in the audience, so the vegan meals should be labeled, so please don't take those unless you know who you are. So, all right. Good. So I acknowledge Joel. I want to also acknowledge Cheryl Shapiro. Cheryl's in the back. Yeah, Cheryl has been absolutely amazing, right? All of this logistical stuff she has done, and she's been a delight to work with. Thank you so much, Cheryl. Restrooms are in the back over this way. There's a photo outside to sign on the table. Some of you have done that. I hope the rest of you will do that too. It's a photo, an image from one of Spiro's spectacular breakout CME models. I think this particular one was from Silvina Guidoni, and of course Judy and Rick and all the others. So please sign that photo. We have the e-card. If you haven't signed that yet, please do, and make some remarks if you feel like it. Yes, Erica has insisted that we have a prize for the best comedian. So she's formed a committee, and they will be deliberating, and we'll announce the winner at the end. Do you have anything more to say about that? Yeah, go ahead. Yeah. Well, I offered 50. I'll crank it up to 100. Yeah, sure. It's just the honor. I mean, think of it. If you could put that on your resume, wow, that would be big. Yeah. So I want to clear up a misconception. Many people are under the impression that we're here in Boulder at this time so I could go skiing. I mean, I don't know how many people have come up to me to say that. Now, indeed, I did go skiing. But when I was talking to Spiro about this, I asked where should we have it, and Spiro said, hey, how about Boulder? How about HAO? Yeah, great idea. So I called up Holly, and Holly immediately said, oh, fantastic, absolutely, we would love to host it. So that's the location. Now, timing, well, this spring and early summer is a super busy time with meetings and proposals and other things. So I said to Spiro, we'll have to have it either this winter or the following fall. So you consulted Mary like you do with everything, and you guys decided, let's do it in the winter. So that's why we're here. And I think it's turning out great, right? I mean, it's beautiful outside, sunny days, beautiful white snow on the Flatirons. It couldn't be better. All right, so I guess that's it from the business to take care of. We'll start the show. Etienne is going to chair the first session. And let me say that we have a crack IT staff here. You control your slides with this device here. The middle button is for advancing forward. The lower button is for advancing or for going backward. And the top button, that's like a laser pointer. You push it and that turns on the light. The light will appear on the monitor. And then you point to where you want to on the monitor. It'll appear there and there. It sometimes works if you point on the screen as well, but not too well. So it's best to point at the monitor. So yeah, with no further ado, let's start the science.
All right, thank you very much. So we're going to start with the science session, and I guess with Ben talk. I think you were Spiro's first PhD student, right? Or among. So it's only fair that you're starting this, and we'll see how you do fare on the comedian challenge.
We will see. Yeah. So is this picking me up? My name is Benjamin Lynch. I'm at the space at UC Berkeley and recently in the EPSS department at UCLA. Right away, it's an honor to be opening Spiro Fest. I realized that the abstract we put in was missing a key element. This is actually, we're going to be talking about the role of magnetic breakout reconnection on the onset and eruption for CMEs. So this is what I'm going to try to cover. The magnetic breakout model for CMEs. We want to know what it is. We're going to overview and fundamentals. I'm going to talk a little bit about magnetic reconnection processes that enable, facilitate, and influence CME eruption dynamics. We'll get into a little bit of fast reconnection and MHD. And what I've called speculative philosophical musings here is, of course, comparison to observations. But really, really, we're all here. The main takeaway of this talk is that the development of the breakout model and the model itself just represents an unbelievably profound combination. Brilliance, ingenuity, and physical insight. So obviously, this is Spiro in a nutshell. So what is the magnetic breakout model for CMEs? What's so special about it? Well, let's examine. So as of last week, we had almost 1,200 citations on the famous Antiochos-Devor and Klimchuk paper. And when you're developing a model for CME eruptions, you've got to do two things. You've got to open the magnetic field in the closed corona all the way down to the pill, or almost all the way down to the pill. So you've got to get rid of all that open flux in order to have an eruption. And the pre-eruption state has to have more energy than the post-eruption state. So it's got to be, the eruption itself is driven by the free magnetic energy. So kind of every CME model has to meet these two requirements. And then the key new feature of the breakout model was to look at it in a multipolar topology so that you could have the interaction between flux systems. And once you've done that, you can get reconnection between the central sheared arcade and the neighboring flux system that enables the whole development of this thing to go forward. And so Spiro once said to me as a graduate student 20 years ago, if you draw a really great cartoon, you don't need to run the simulation because you can explain all the physics in the cartoon. So, okay, ADS is sort of spoiling here, but we're going to go through the cartoon and the schematic of CME eruptions that has had the most influence on our field of research. Except this is not it. This is tether cutting. So we're going to get back to tether cutting, but of course we're here to talk about breakout. So what happens in a magnetic breakout eruption? So you've put your energy here on the central polarity inversion line, and you've inflated the central arcade. And so I've kind of colored actual simulation results. I'm going to talk about this like a cartoon, but it is a simulation. Once you've energized the central flux system, you've got this expanding shear field. It's inflating in response to that additional magnetic energy you've put into this system. And this upper null point here on the corona, which is at the intersection of the separatrices that divide these flux systems, gets distorted. You build up current. With this continued expansion, you're driving inflow into this current layer. You get reconnection, this blue and red flux to be transferred into the side arcades. And so you're removing the restraining overlying flux. The more you remove it, the more the arcade expands, the faster those inflows into this reconnection region, and you just inflate out. You build up this current layer deep in the shear channel, and eventually you get reconnection here as well. This is kind of the standard CSHKP scenario down here. You pinch off, you turn your sheared arcade into a flux rope with this flare reconnection, and the system has figured out a way to remove all that sheared field and eject it to infinity. And if you just look at kind of this scenario here, you really have to kind of appreciate that the whole standard tether cutting CSHKP kind of scenario, it's embedded. It's embedded in the breakout model as we've discovered. I've already destroyed the pointer. Fantastic. So, taking a step back, we've got to do two things. We've got to open the field down to the polarity inversion line, and we've got to have the ability to go from a higher energy pre-eruption state to a lower energy post-eruption state. And so if you've got a bipolar arcade, there's only one way to do that. If you grab the very innermost field line and you drag it out to the edge of the heliosphere, you've opened all the flux. Pointer is going to have to be resolved.
Just drag to the right. Press and drag to the right. There we go.
Okay, so if I point at this wall, I can get it to come up here. Fantastic. So I've dragged this field line all the way out. I've opened the entire flux system here. Now, in the multipolar scenario, you've got two options. You can first do the exact same thing, where you grab this innermost field line, drag it out to infinity, but I haven't allowed any reconnection yet. So I've got to open all of this overlying red flux and all of this overlying blue flux in the inner arcade. This null point here in the corona has now been stretched out to the edge of the heliosphere. And so that's what happens if I don't allow reconnection. If I allow reconnection, I can get this red and blue flux to reconnect and end up in this side arcade. I can still drag the central field line all the way out to the edge of the heliosphere, but now instead of opening 2 entire additional flux systems, I've just moved all that flux out of the way. And so this is a lower energy state than the state that had all of those flux systems open. And so what does that look like? Plot energy. So there's a state, there's an energy associated with this kind of maximally open field state. And so in a bipolar arcade, you can run an MHD simulation and you build up all this energy. You've pumped in at the equatorial polarity inversion line. And if you don't allow reconnection, you stay up here at about the open energy state. But once you get reconnection, you've given the corona a pathway to get to that lower energy state. And so it turns out to be energetically favorable to reconnect and get this stuff out here. In the breakout scenario, it's exactly the same thing. So you have a maximum energy associated with opening all of that flux, and a kind of lower energy state where you've reconnected all the flux, but you've still managed to open the very lower lying layers of the shear channel. So you build up your evolution here, you approach this maximum energy, and reconnection allows you to get down to a lower energy state. And in the very nice simulation that we can all sign a snapshot of outside, Judy Karpen showed that here we have the rapid release and transfer between magnetic energy and kinetic energy of the eruption. So we've done the first 2 things that we need to do for every CME model. And the reconnection is the mechanism for going from your pre-eruption to post-eruption state. So what happens when you've got these driven systems? Well, over here you can see just the incredible amount of detail that comes out of these reconnection processes. And in fact, this detail shows up because you've kind of over-constrained your system. The current sheet size is determined by the system. The inflow velocities are determined by the system. You've got this whole coronal response to trying to process all this flux, mass, momentum through this current sheet. But the current sheet is given by the size of the system. So you have to come up with some way to process all of that material and magnetic field through this current layer. And the sun and the MHD equations figure out that if you break up the current sheet into lots of little islands, that's the way you get quote unquote fast reconnection in MHD, and that's the way you process all this stuff through. And so once you've noticed that, then you can run all sorts of simulations. You put your grid points on the current sheet, and sure enough, everywhere you look, there's tons of these little islands. There's just so much detail here. And you can do a lot of things with these islands. You can count them, you can look at the X points and the O points in the current sheet. You can calculate things like flux into the current sheet, carried by the inflows, and flux out of the current sheet, carried by the outflows. And you'll notice that the flux coming into the reconnection regions, okay, it's highly variable, but the flux coming out is even more bursty. And so there will be a bunch of talks later today, including by Marcel Corchado on sort of the dynamics of why flare reconnection can be bursty. Lastly, well, second to lastly, we want to figure out if these simulations represent reality. We want to test how much physics that we know we've put into the models correspond to reality. So this was one of my papers as a graduate student at NRL, back when the group was there, where we took this very nice 2.5D simulation, and I sat down, I was learning computational physics, and so we tried to figure out what all of the observable signatures that came out of these simulations were and could be. And so I remember counting pixels here about to figure out the height of my flare arcade, and so here we are as a graduate student, back when we wrote everything down, calculating how fast the ribbons separated, how high those loops went. We were at NRL, so it was like, we've got to compare to coronagraph observations, and so we did these synthetic white light images to kind of show that with the breakout model, you obviously got the three-part structure of CMEs. We wanted to look at the internal field structure of the eruption, and so we fit one of these linear force-free cylinders to the model, and sure enough, even by 15 or so solar radii, you had a very smooth rotation in the fields. Okay, this was actually one of my favorite projects as a student. Someone else did all the hard work of running the simulation, and I just got to try to match it up to the observations. Okay, I'm still doing exactly the same thing, but the simulations have now gotten a lot better. So over here, this is Peter Wyper will be talking about pseudostreamer CMEs. So this is synthetic EUV emission from a CME launched from a pseudostreamer. And the observations are finally catching up to the sophistication of the models. We're now starting to fly through the simulation domains with actual spacecraft and take in situ data. And you can figure out, okay, what would this thing look like if it was Parker Solar Probe flying through one of our simulations? And so here you have synthetic white light that the Whisper camera would see. You've got in situ magnetic field profiles. This particular trajectory through the simulation is a kind of glancing flank encounter. And you can see that as we've drawn the instantaneous magnetic field connectivity to our synthetic observer here, none of these field lines look like a coherent flux strobe when you watch the simulation. And if you look at the in situ data, you've got big spikes and rotations in the field. Here we're seeing a large velocity spike of that first shock and the material that follows out here. This is a really great time to be doing this kind of comparative simulation work. And so the magnetic breakout model is just absolutely everywhere. And in fact, it's places like every event that we've ever looked at on the sun happens to be multipolar topology and a candidate for the breakout model. But it's also in unlikely places. So for example, this guy took one look at the breakout model and was like, I'm going to build a plasma thruster for spacecraft. And so he sat here and actually built some device and ran some simulations for it. And this is kind of, following the homologous CME idea that Rick and others have worked on. Okay. Someone else was interested in relativistic CMEs for magnetars. Took one look at the breakout model and said, that's how we're going to work. So this is pretty, you can judge the impact of something by kind of how many other fields it touches, and we've seen that with the breakout model. But even more unlikely, sort of stranger than laboratory plasma physics, astrophysics, stranger than kind of bizarre astrophysical plasmas. This is a simulation that my wife, Erica Alpermerio, who was at Predictive Science Incorporated, ran. Now, of course, they inserted flux ropes, and so she was looking at CME interaction. They launched. Here they are running into each other. But that looks a lot like Breakout to me. So she actually discovered Breakout by inserting flux ropes and having them erupt. Okay, this isn't exactly our scenario, but we did call this anti-breakout reconnection back in 2008. She essentially launched the two side arcades into each other. Tibor Tworok was looking at also from Predictive Science Incorporated, was looking at a model for coupled sympathetic eruptions. And okay, they have 3 quasi-stable flux ropes here in a row. They've erupted one, but sure enough, that disturbance starts the breakout reconnection over here, and then you get the CMEs moving. Slava Titov, brilliant theoretician, I think also at Predictive Science, was looking at bipolar eruptions and figured out that actually, even in bipolar arcades that they've put a flux rope in and erupted, you get this kind of reconnection that recycles some of this overlying flux through the ejecta and then out one of the legs of the CME as it progresses. So they called this breakthrough reconnection, which is analogous to breakout reconnection, except it's in bipolar regions. So that was our one requirement for the breakout model. We had to have multipolar regions. And the folks at Predictive Science figured out how to get it into bipolar arcades. Fantastic. So to summarize, this is just a great model. It's a reconnection provides the channel from higher energy to lower energy. There's lots of detail in the reconnection process to look at. But really, it's just been a pleasure to work with the whole ARMS team, Spiro, Rick, Judy, Jim, over the last 20 years. And I thank you very much.
So I was going to say, Ben, beautiful results there, especially your stuff on the 3D simulations, comparison to observations. Do you think that we're in a position now where we can look at the models and do the comparison before the eruption? The problem is with doing the comparison after the eruption, first of all, they more or less all look the same, right? Because you're always going to get the plasmoid, you're always going to get the flare reconnection, et cetera, et cetera. And also it's kind of messy. It's really cool to look at. But if you want to do things like space weather prediction, you have to start looking before the eruption and see if we can find any kind of distinguishers from the models to allow the space weather folks to predict CMEs. That's really our next challenge.
I certainly agree. And if you've got the right kind of pre-eruptive configuration, then I think you ought to be able to see signatures of that breakout reconnection in either like pseudostreamer stalk poofs, kind of before the thing erupts. But you're right, we do have to do better at tracking the energy buildup and looking for kind of precursors. Because we can say that active region has a ton of shear on that neutral line, looks really complex, it's evolving fast, but we can't yet say when. And so we do have to really dive into these simulations.
Would you say a bit more in the outward plane direction? Like this in-plane direction is really beautiful. And I'm curious, and I think that has a lot of space weather application as well. When you look at the outward plane direction, like the flux rope foot point, do they continue to anchor at where they were after post-eruption? And how well, like your model could help us visualize that, if you could say?
Yeah, that's, we've looked at some of that. You definitely see dimmings where you expect the CME foot points to be. And we do see that in the 3D simulations. And those evolve in time, and you can watch the sort of the CME foot point connectivity evolve and move across the surface of the disk and eventually end up at the nearest coronal hole in their respective polarities. And that should have in situ signatures with electrons and all of that. I mean, I agree, that's a very important thing to look at.
All right, thank you very much. We're going to move to the next talk. A long-time collaborator of Spiro, Judy, going to talk about the role of magnetic topology.
Okay, well, this is a total honor and a joy to be able to speak in Spiro's, it's coming out of here, to speak in honor of Spiro at Spiro Fest about one of his favorite topics, topology, which is a study of place or study of location. So it's very appropriate that that's one of his favorite things. For some of the rest of us, it ties us in knots. But, sorry. So I'm going to, thank you, Ben, for such a wonderful introduction to the breakout model. I'm going to be mainly focusing on how topology plays a crucial role in breakout and give you an example of a very recent analysis that Pankaj Kumar and I and the rest of the team did of a very unique, well, hopefully not unique, but very unusual looking configuration that involves topology in two ways. So one of Spiro's really seminal insights was before 1998, but he didn't get it into a paper until 1998, was that one of the crucial configurations on the sun is the so-called embedded bipole, also known as a fan spine topology. And this is simply a minority polarity surrounded by majority polarity. And the lines that are shown here, and let's see if I can get this thing to work. Yeah. So these are field lines. Here's your minority polarity in the center. Majority is just surrounding it. The other side of the bipole basically merges into that other majority polarity. And here's what they call the fan, which is sort of the dome enclosing all the closed fields. And the spine is this linear structure. It's kind of a singular structure, feature that goes both down to the surface and goes out either into a closed field, which means it closes back down on the surface, or heads out into open field, depending upon what the surrounding field is like. Another structure that is very important, I'm not going to be going into gory detail because Peter is going to be talking about pseudostreamers, and Ben already introduced them as well. You can sort of think of this roughly as an extended or a set of extended embedded bipoles. They're surrounded, again, by majority polarity, but it's much more complicated than this single null and single spine. You usually have at least one spine, but you could have multiple spines surrounded by this fan that extends out into open field. So, all right. Why is this topology important? Thank you, Wikipedia. This is an example of what topology sort of deals with, is how you can look at the invariant properties of structures as they evolve under different stresses and strains. As Ben pointed out, eruptions require both energy buildup and rapid release. And if your energy buildup is being bled off while the energy is building up, you're not going to get an actual eruption. You're going to get some kind of little puffy thing go off. So the advantage of this configuration is that you have both internal and external strapping fields that are allowing the pressure, magnetic pressure, and so on to build up through photospheric motions or through emergence or other processes that the sun naturally does. Then the only way to release this really fast is through rapid reconnection. But for that to happen, you need a current sheet. Thankfully, null points are a great place to get current sheets. So null points, these embedded bipoles, and the similar structures are all over the sun. They're in coronal holes, they're in active regions, they're quiet sun, etc. And any pressure, either due to foot point motions, again, due to emergence, cancellation, whatever you want to call it, all of these processes can give you current sheets immediately by affecting the null. And that gives you locations that are natural locations for reconnection. I just wanted to state that the breakout model requires this topology, but it doesn't, it basically doesn't work without a null, except for the examples that Ben gave of pre-existing flux ropes interacting. I just wanted to say that HN is going to be talking about this configuration more in talks about jets, and other talks are going to come up about jets. Peter's going to be talking about pseudostreamers. You're going to be seeing these type of configurations again and again throughout SpiroFest. So this is the example that I wanted to start with. This was a really interesting event that Pankaj found. So it's basically a set of nested nulls. There's an active region in here, small active region. Think of this as the configuration that Ben showed before, the quadrupole inside. And then there's this big pseudostreamer outside here that's rooted, on either side of the equator, pretty much. This is the stereo view here. And you can see that there's a large pseudostreamer off the limb from that view, and the active region is, somewhere. Okay. Just to focus in, we did a potential field source service model around just to prove that there are nulls in here, and around the inner active region. There's a null somewhere right around up here. The dash line rough, whoops, go back. Way up. For some reason it just jumped and now it's not going back. You guys can help. No, go back one more, please. Thank you. Wasn't even touching that button. Okay, so this is and then this is kind of a larger view to show you that there really is a pseudostreamer null up here. And it's also offset, so you can see that the spine actually does not land, inside the active region. It's off to one side of that. So this is an interesting configuration. What happened in this configuration is that it got a whole bunch of little bubbling around B-class flares, and then it had this eruptive flare at the sort of toward the end. What we're showing here is the 304, sort of 100,000 degree plasma. I put a rough dotted line around where the separatrix, the foot points of that fan spine, the foot points of the fan are located. And this is just showing you what's going on when the eruption actually occurs in the inner spine system. There's very little change in the magnetogram. This is at the plus or minus 100 Gauss level, which is because it's an active region that's appropriate. But so you don't see a whole lot of evidence for flux cancellation, but there isn't a heck of a lot of energy built up in there. So, obviously photospheric motions are able to do it, whether or not they really believe that flux cancellation is going on. This shows in larger view what's going on in the hotter, million degree roughly temperatures. And you can see again down here in the built up region, this is sort of bubbling along, and then you get what looks very much like a flux rope, but then it stops. It gets all the way out to a little out of this frame, and then you see the material kind of fall back down and not really do very much. So it starts out very much like a 3D breakout event. We see plasmoids in there. I would focus in on here. You can see in this general region plasmoids coming out. You also see plasmoids going down along the sides, going down toward these lobes that Ben showed in his talk. But then there's also some other interesting stuff going on here, which is that it starts out with one foot point in the flux rope up here, and then that kind of disappears, and you end up with just the southern foot point and a new foot point going on down there. That's kind of weird, and when we first saw these observations, we said, boy, that's really interesting. So as I said, it's just sort of a typical breakout event. You get the flare arcade underneath. You get the flux rope heading out. There's a filament involved in there, the dark material that's right here. But that isn't the whole story. So this is just sort of summarizing what the structure is. You can see the filament itself, that most of which starts to fall back down. The flare arcade. This is the flare current sheet. Looking at things in 3D is a little more complicated than a lot of those 2D pictures that are much more much clearer and much less complicated. Thank you. But in the second phase, so it starts out, as I said, like a regular breakout event. But then in the second phase, you see this switch of foot points. You see the again down to here. You see the flux rope itself stop, and I'll show that again in a minute. And so this didn't proceed. It was basically an stalled eruption, is what we're calling it. So these are just three images from stereo B because from that viewpoint it was off the limb, and you can see that it was heading out. And this is just showing the cool material again. It heads out, it looks like it's kind of hitting a wall. You can see here already the north leg has disappeared, and then it's fragmenting and kind of falling back down. Finally, why do we say this is kind of a stalled eruption? Well, you do see a little shock coming out. Oops, wrong thing. Okay, you see this little wave, little shock coming out, and a little bit of an ejectum. But basically, once you get out into the coronagraph, there's very little to see. There's just sort of the remains of the front, and there isn't a whole lot of an ejectum. This is a better view of kind of the wave and the whole thing going on. You can see the wave ahead of it, and you can definitely see the material falling back down. So what's going on? Well, of course, to understand the physics, we have to do 3D simulation. And this is all courtesy of Peter Wyper. He actually did 3 simulations with changing some of the magnetic field strength parameters. I'm just going to show the Goldilocks one that actually looks very much like the observations. Again, this is the configuration that we're looking at. Here's your little active region. Here's your pseudostreamer surrounded by open flux. Movie here that needs to be clicked on. Thank you. Okay, so you can see this should repeat, I hope. So you can see the eruption starting at the flux row, you can see the shock coming out, but then you can also see that it, once it gets into the pseudostreamer, things kind of, get tangled up, and this is just showing, and it stops at the breakout current sheet in the pseudostreamer. You do see a weak ejectum coming out, and you also see kind of mode conversion going on with this shock. Part of the shock heads out there, part of its shock heads out along the spine. If we look at it from another point of view, if you could click on this one too, please. This gives you a little more of an idea of what the field lines, the field itself is doing. And I was hoping to stop it at one point and show what was going on. But one of the things I wanted to particularly show here is that, again, as we saw in the observations, the foot point of the flux rope changed dramatically from where it was originally inside here all the way out to another location that's rooted in the pseudostreamer polarity. You can also see that the field lines inside are kind of wiggling around but not really getting out. So let me move on. So to summarize, so we do see all the observed, model signatures from a typical breakout event, but then why didn't this become a major eruption? And the main reason is, and again, this was Spiro's brilliant insights, is that when you have these nested null configurations, let's see if I can, the orientation of the field, once this flux rope starts to come out, it gets into the pseudostreamer, but then it's not oriented properly for further breakout reconnection to occur. So unlike, the situation here where it's always oppositely or anti-parallel to the flux, it's going to end up more or less parallel, and then you're in trouble. So another factor that Peter's noticed in his calculations, because he did more than one calculation, is that the strength of the overlying pseudostreamer field seemed to make a difference as well. In either case, you get very little reconnection at the pseudostreamer current sheet. That seems to explain, at least in this case, why you don't get a full eruption. So how common is this? Okay, any place where you get bipoles emerging into pseudostreamers or perhaps into simple active regions, depending upon, again, the orientations of the field. And this paper was just accepted last week by APJ. So thank you.
Thank you, Judy. So I guess there is always one question that Spiro need to ask, right?
Yeah, he can't ask.
So when Spiro doesn't ask questions, Jim need to ask.
This is the question that Spiro fed to me earlier. Yeah, no. No, so I've often wondered if you see foot point signatures of the breakout reconnection at the side lobe foot points, and it looks like some of your bullets are saying that you do.
Yeah, I mean, you definitely get the sort of the circular ribbon, you know, on the what do you call it, the base of the fan. And so, yeah, you're getting, and that was something that Alphonse pointed out many years ago, was these so-called sprinkles. Sprinkles, is that the right word? What did you call it? Crinkles, sorry, one of those things. And we've seen that in a lot of jets and a lot of other, you know, configurations where you can see fairly clearly down to the surface.
How about with big flares, big events, big CMEs? Do you see nice ribbons at the side lobes?
Somebody like Jiong is probably better equipped to tell me. I mean, I've only been involved in a few of the really large flare analyses, and yeah, we have seen at least pieces, not necessarily the entire circle, but there are these things called, you know, circular ribbons that people talk about in somewhat larger, you know, eruptions that are all the same thing.
Judy, it's also a question to Ben. At some point in history, some of us are trying to find signatures to distinguish between breakout and tether cutting reconnection, namely trying to find if there's any energy release or any signature of reconnection above a fracture or below. Do we have any conclusion in this front, on this front, years after that attempt?
There have been radio reports of activity above, you know, at where you'd expect the breakout reconnection to be occurring. I haven't seen a lot of them. Have you seen, I don't know if you've seen anything more recently. Oh yeah, and the other thing that, you know, Jiong has been involved in is the observation of dimmings above the breakout null that precede the eruption itself. And so there's a couple of papers, you know, recent papers in the literature on that. There's a number of things, but we can, sorry, I don't want to take up much more time, but.
Yeah, this is a very important point, and this gets back to what I was commenting with Ben. What we need to do is to look at the early part of the simulations. Never mind the part after the eruption starts. We need to look before the eruptions and see what exactly are the signatures for kind of, you know, typical events, and then look at the observations to see what we can do.
And we've done a fair amount of that with the jets, you know, because they're easy to see, but there are eruptions.
Remember that.
No, there was more questions, but you're done with it?
You know, this is not necessarily a question just for you. It can be for anyone. But so you start off at showing the observations and all the complexity. Then you jump to the simulation, and it kind of qualitatively matches there, right? But how far away are we from being able to do real data constrained simulations here where we can use the observations as an initial condition and really see how close our simulations are to reality?
Are other people out there who, you know, done mostly we've focused on trying to getting into the really messy.
Hi, Judy. I want to focus on your most important slide. How does Wikipedia get an adult cow that can't eat?
There's also a mug that transforms into a, whichever one you like.
Thank you very much, Judy, again. I think the next speaker is... That's you.
So this go for 15 minutes. I have 15 minutes only. Okay. Yes, all right. Okay. Okay. Thank you for giving me the opportunity to speak here. It's really. So I'll be talking about our recent work on MHD simulations to simulate CMEs going from produced from prominence cavity systems, as well as recent development of data-driven simulations to model realistic CME events. And listed here are my collaborators for the work I'm presenting. So we all know that large-scale quiescent filaments and prominences are major CME precursors, and when observed above the limb at the correct projection, they often show this kind of a cavity surrounding the prominence, and which can be seen in both white light coronagraph observations as well as EUV images in hot coronal temperatures. And sometimes in the cavity, you see this kind of a horn, U-shaped horn structure extending above the prominences, as seen in these images. And these movies show that the prominence cavity system can undergo slow rise for many, many, many hours before they approach eruption. And as the undergoing slow rise, when they approach eruption, the prominence horns gets more prominent. So one of the suggested basic underlying model for prominence cavity system is that it's a magnetic flux rope with containing helical fields with the prominence condensation supported by the dips of the helical flux rope. And so to study that, we have carried out MHD simulations to model prominence-forming coronal flux ropes under coronal streamers. And our code solved the following MHD equations with the energy equation explicitly taking into account the important non-adiabatic effects in the corona, which include field line heat conduction, and empirical coronal heating that depends on height, and also optically thin radiative loss, which can drive thermal instabilities to cause the formation of prominence condensations. And we carried out simulation in this spherical wedge domain given here, and we initialized the simulation with helmet streamer solution, where with an ambient solar wind driven by the accelerated and heated by the empirical coronal heating. And for the low boundary condition, we assume a fixed coronal transition region temperature of 500,000 Kelvin and adjustable base pressure, time-dependent base pressure that is driven towards a value that is proportional to the downward heat conduction flux, as described in Withbrow. And we also impose at the low boundary the emergence of a twisted magnetic flux rope. So here is the simulation result. In the various panels, it shows the magnetic field and also the synthetic EUV images, AI EUV images in various channels and from various different perspectives. And here shows the evolution where the flux rope is emerging into the corona, and emergence stopped while the prominence condensations form at the dips of the field, and coronal cavity forms when we viewed along the direction of the flux rope, and we see a prominence horn forms, and the prominence drains. So it maintains in equilibrium for a long time and undergoes a quasi-static rise. As it rises, you see the prominence horns becomes more prominent, and eventually it undergoes eruption, where you see significant draining of the prominence. So here are the evolution of one field line colored in temperature, pressure, and field line flow. So in this case, the prominence condensation forms sort of in situ in the dips. When the dips emerges, it's in coronal temperature, but it carries relatively dense plasma. So radiative cooling causes thermal instability and collapse. It forms prominence condensation in situ. In reality, it's probably flux cancellation causes the dipped field to form and make the thermal non-equilibrium caused by foot point heating can result in formation of prominence. But here, in this case, it was basically we make it form because of the high density at the dips. And once it's formed, it drives a flow converging towards the dip. And it causes a sudden drop of the pressure at the dips, which caused density depletion of the upper part of the prominence-carrying field lines, which caused the formation of prominence cavity. So shown here is a side-by-side comparison of two simulations with the same flux emergence and pre-existing magnetic field configuration, but with the right-hand side case where we suppress the prominence formation by changing the radiative loss function and also enhance thermal conduction, so just to suppress the prominence formation. So you can see in this comparison that both cases, flux emerges, left-hand side one forms prominence, the right-hand side one without prominence formation, and the twist emerging coronal is in total of 1.8 which is above the critical limit for the kink instability. So as a result, it's almost immediately accelerate, as can be seen in this rise velocity, while the left-hand side case is stabilized by the weight of the prominence, and it pretty much stabilized for many hours and undergoes slow rise as the prominence drains. So it eventually erupts. So the point is that the weight of the prominence really significantly changed the stability of the flux rope. So here shows a zoom-in view of the evolution of the prominence cavity during the quasi-static phase. And we see the formation of the cavity and also the horn, prominence horn. Oops.
Press and drag to the right.
Anyway, okay. Well, you can see it, and then the prominence horns gets more prominent, form these kind of sharp structures that indicate, like indicative of the dip of the helical fields. I'm going forward. Okay, so we try to identify the magnetic field structure corresponding to different emission features in the cavity in UV. And so we find that the prominence cavity corresponds to the upper density depleted portion of the prominence carrying field lines because of the load pressure at the dips. And the prominence horn is made up of field lines which have shallow dips with the dips right at the upper edge of the prominence where the prominence condensation is evaporating to coronal temperature, but still pretty dense. So it gives this bright horn structure, whereas the core cavity in the middle, enclosed by the horn, corresponds to really hot field lines, twisted field line that does not contain prominence. So basically, it seems that a coronal magnetic flux rope structure with helical field lines can reproduce qualitatively the features of a prominence horn cavity system for quiescent prominences. So, okay, in this case, in previous case, it's an idealized configuration to understand the large-scale prominence cavity system. So, but we have recently also worked on development of data-driven image simulations, use observations to study the complex magnetic field evolution of realistic event. In this case, we have devised a new low-boundary driving electric field based on the observed normal magnetic field evolution and vertical electric current to model and apply it to model the event, this particular event of X-class flare from February the 15th, 2011 from active region 11158, which was a well-studied region. So, so the low boundary electric field we use to drive the simulation contains three parts. The first part is so-called the PTD electric field derived by Fisher, where we can invert a horizontal electric field which will reproduce the observed normal magnetic field evolution. And the second component is called the twisting electric field, computed based on the vertical electric current observed in vector magnetograms, which effectively corresponds to a vertical transport of a divergence-free horizontal field with the observed vertical current into the domain at a specified speed. So this is the one that's energized the coronal magnetic field. And the third component is so-called a random electric field, which is actually inspired by the so-called stitch electric field, okay, developed by Spiro and collaborators to model holistic condensation. But here we used a field that is, where this Cassie field here is a random superposition of randomly placed cells of opposite signs to drive random motions, random twisting motions of the foot points of the flux concentration to drive background coronal heating here. It doesn't drive any twist into the corona. So, okay, so we start out with the potential field and then relax it to a steady state with the random electric field, and then to reach a hot corona, and then we drive the with all three components of the electric field, so that we can see the field are being sheared and twisted, and by the twisting electric field, and after a period of 1.5 hours of a quasi-static buildup of the free magnetic energy, we see the development of several eruptions, as indicated by the sudden release of magnetic energy and sudden enhancement of the kinetic energy. And here it shows the outflow in the central cross-section resulting from the eruption. So the pre-eruption magnetic field shown here with the current, colored in current and twist rate, shows that the pre-eruption field builds up, shows highly sheared sigmoid field with different signs of twist. In the middle is positive twisted, and then the one connecting to the following polarity is negative twisted. And these current carrying fields show morphology similar to the observed UV hot channel images, and the synthetic images in the middle also show some qualitatively features consistent with observations, mainly in the central sigmoid formation and the large loops connecting the major polarity concentrations. And we find that the pre-eruption magnetic field that build up in the simulation is consistent with that of a nonlinear force-free field extrapolation, with field being force-free and with the vertical electric current at the bottom boundary pretty consistent with the observed ones for the large-scale patches. And here shown here is the erupting field, and we find that it's initiated by the sudden onset of eruption acceleration by the sheared sigmoid field in the middle central polarity inversion line, but eventually it developed into the complex structure with two flux rope of opposite twist and also different polarity connections at the bottom. And here we did synthetic image, calculate synthetic images in 170 AI 171 angstrom, but viewed from the stereo perspective. And we see the outgoing two distinct structures, and here the middle is the running mean difference, and compared to the observed stereo UVI 171 running difference, they show similar two distinct features going out, but the one in the middle, the simulation is severely constrained by the simulation domain, so further improved simulation with bigger domain is necessary. And in particular, in this case, we find that the pre-eruption field is over the polarity inversion line are strongly sheared fields with no dipped field lines, as shown in the curvature evaluation on the right-hand side, and that most of the current of the sheared field is still below the height where the critical for the rate of potential field decay to reach the critical value of minus 1.5 for the onset of torus instability. So in this case, it suggests that the eruption is actually triggered by the onset of tether cutting reconnection, which form a flux rope during the eruption, as you see the curvature changes when the flux rope forms. So, conclusion. On image simulations of prominence forming flux ropes suggest that the observed quiescent prominence cavity horn system is consistent with the of magnetic flux rope with helical field lines. And different we can identify the magnetic field characteristics for different parts of this. But and also for the case of this data-driven simulations of the of complex magnetic field evolution for the CME event, we find that it's formed highly sheared field lines, which show good qualitative agreement with the brightening loops in the SDO-AIA, but eruption is triggered by reconnection and flux rope formed during eruption. And then we find that this twisting electric field derived from the observed vertical electric current is a good way, a promising way to drive image simulations to establish the force-free pre-eruption coronal field and model its subsequent dynamic eruptions. So the result is published in this team paper, LWS team. So that's it. Thank you.
Thank you very much. Questions?
First question.
Thank you, Yuhong. Excellent talk. Very interesting work. There's a little bit of a disconnect, though, between your top and the second conclusion, because the top you say that you need German simulation before the eruption, German simulation before the eruption, before the reconnection took place. You didn't really see helical field lines, right? They were primarily strongly sheared with no dip.
There are dips in the horns. Those are dipped field lines.
For the data-driven simulation?
Not in the data-driven
Right.
simulation is consistent with a sheared arcade.
Exactly right.
And a reconnection from the flux. I'm just saying they're both cases. They're both these models.
Okay. I mean, well, it's true we have two models, but what I'm asking is that from the data-driven simulation, you did not see many dips. The observations from that event, though, were they consistent? I mean, if you looked at the prominence, if you looked at the structure, second one. Right, but the observations, if you were to look at that structure, would it look like, you know, a standard prominence with the cavity, with everything, with all the trimmings?
Thank you. So first of all, a comment, and it's because you mentioned the slow rise. I think that your first one, at least, didn't have the breakout reconnection at the top. And if it did, and this addresses a point or a question being asked by Spiro and others earlier, if it did, then early on you would get the breakout reconnection starting, and you would get the side lobe starting that Ben talked about earlier. Actually, we've seen that before in a very slow rise, a quiet region filament eruption lasts about 6 hours or something for the slow rise. And you can see these side lobes developing during that time. In the x-rays, it looks hot over there because you can see the hot loops building, and in some EIT lines, I guess, it's dimming because you don't see it there. So anyway, that is one way that we might check for breakout. And so a question I have for you is that at this meeting, to have an eruption model without breakout, isn't that sacrilege?
No, it's important. It's critically important.
Keep it honest. I agree. I agree with you. Good point.
All points of view, even incorrect.
Yeah.
Nobody has the answer. I guarantee you that.
Yeah. Okay, sorry. Yeah, I think that for these quiescent large-scale filament channels, large-scale prominence cavity systems, you know, you see these horn structures. That it is indicative. I think it's consistent, at least, you know, for the simulation. It's consistent with probably a helical flux roll. So.
I think I'm going to lead into Manolis' talk, actually. This is a question for you and also for Judy and Spiro and the modelers and Ben. You know, when we watch active regions, you were talking about driving for about an hour and a half, and then it would erupt. When you watch active regions, or you watch the coronal, the quiescent filaments, they don't erupt often. You know, generally speaking, they don't. If you want to look statistically, they don't. So are we at a time yet with the simulations where we can start to really examine when something is going to erupt and when it actually does not erupt? I mean, that is part of the challenge, is can you drive it and have it not erupt? You know, that sort of thing. So.
I drive, yeah, it's actually hard to make it erupt. That's the thing. We've been driving it. If the electric field is too weak, numerical diffusion killed the, it's actually, we're trying to mostly understand the 3D magnetic field during the eruption. That's the pre-eruption field configuration, as well as, right now to time it is difficult. It's very difficult because of the reconnection sets in when it's really highly numerically dependent. I mean, in terms of the
Let me
schemes.
separate the two issues that you raise, Katie. Driving the simulation for the many days or the days before eruption, no, you can't do that, but you don't really need to do that. However, identifying from the simulation signatures of when the thing will erupt, that is critical. That's really what we're going to do next.
Ike, thank you very much, Yuhong, again. The next talk will be given by Manolis Georgoulis, in which, in order to fit with the arms team, he's talking about a smoking gun.
Right. So I proceed with this?
I think so.
Oh, right, okay. All right, well, thank you. And thank you, Katie. That was a great introduction indeed. And it's been a huge privilege for me to stand here before you on behalf of the others to be here and Angelos, who can. I'll try to talk about active regions, and I'll try to talk about major eruptions and how do they occur from active regions. So I'll give you an idea of where we stand or where we think we stand, and then I'll be talking about the smoking gun, if any. So that's an outline. The debate that we all know about sheared arcades versus magnetic flux ropes, and the reconciliation apparently after a couple of decades. It didn't take too long, but we had something that, you know, allows us to be kind of compromising between the two different situations and making sense out of it. And then helicity, omnipresent. And we believe that if it was not helicity, we wouldn't have any of these to discuss. Then making sense of what causes all these kind of things, and this is another contentious topic, Lorentz force. If it plays a role, and what kind of role does it play? What do we need to make sure that it plays or it doesn't play a role? And finally, some conclusions. So you see two active regions here, active region 1158 on your right. This has already been shown. Pretty dynamic evolution in there. An active region 11093 on the left. Not that much, one single eruption, about 50 times less flare productivity than the active region on the right. You have some flux emergence on the left as well. You get a filament eruption out of that, but on the right, you can see conspicuous evolution of both polarities closely packed on the photosphere and apparently heavily interacting. You get shear for free in situations like that. If you have strong polarity inversion lines on the photosphere, and I will explain what I mean by strong, then shear is there, present at any given time, okay? And we ask why. So on your left, you see the iconic picture of a sheared arcade that Rick and Spiro came up more than 20 years ago. Clear. This sustains the filament channel that you have above the polarity inversion line. And then a few years later, you had the other competitor, a flux rope type of situation above a similar polarity inversion line in which you have coiling around kind of a core that is less twisted in this situation. So what is this, one or the other? And I'm sure you always remember countless discussion over the years about what is it, the one or the other. So Spiro, the other Spiro, had this idea and he put together this artful picture so that you see what key players have in mind. That was an easy team some years ago, tried to come up with a compromise or something that allows to a common understanding between the two pictures. And there was a verdict that was captured in the Space Science Reviews that says, listen, don't put your eggs on the one or the other basket. It's everything in between. It can be a hybrid structure. Yes, you start with shear for free, but then if you let it evolve in the course of time, you're going to be getting a magnetic flux rope. And the situation has a certain direction from the sheared arcade to the magnetic flux rope, not the other way around, which points to an irreversibility in there. And then we had more. This is a very recent simulation that I came up recently that shows this kind of thing in action. You have a polarity inversion line. This is data-driven. You have something that points to a CR arcade, and then in the course of time, you have a magnetic flux drop that you see kind of shown here in blue. That's one thing, irreversibility. And the second thing that you see from this simulation is that the whole thing is kind of bubbling up. It is gaining height into the corona. And you need to ask yourself why this kind of thing is happening. And why do you have a reversible evolution from a sheared arcade to a magnetic flux drop? This is another indirect evidence, and it's far from unanimous. This is my way of understanding things. What you see, I can make it work. Yeah. So what you see over here, you see a situation in which you have active regions giving flares, confined flares and eruptive flares. Confined flares are in red, eruptive flares are in blue. And indeed, we focused in the pre-eruption situation, pre-flare, pre-eruption. Time 0 is the time of the flare or the eruption. These are a few hours before. You see a mesh of different evolutions, and what you see on this axis here is the force-free parameter, the alpha value on the area of the polarity inversion line of the active regions. You start seeing something over there which comes pretty clear, and it starts jumping out at you if you take a superposed epoch analysis of the eruptive active regions, flares with CMEs, and the non-eruptive ones. What do you see there? You see that the alpha value, the force-free parameter, hours before the eruptions seems to decrease, and then all of a sudden after the eruption, boom, jumps back to pre-eruption values and even more. Is this losing something? I think that not. We're not losing something here, but because we are restricted to be looking at the photosphere, what we see there is the bubbling up of the situation, the bubbling up of the structure that makes the magnetic field more vertical, so you do not have that strong horizontal signal to give you a strong alpha value. And when the eruption happens, after the implosion of the magnetic field lines, you get it back. You get the signal back. That allows you to get your alpha value in the photosphere. And you see with the red curve over there that you do not see anything like that in the active regions that flared, but these flares were confined. This is still TBC, as you see over there, and this is my kind of interpretation. There might be different in this particular situation, but this is very recent. So this is in progress, in essence. So helicity. In that EC meeting, there was a lot of discussion about magnetic helicity, and we showed the result over there in which we were able to see the interplay between the mutual helicity and the self-helicity. The self-helicity in a structure is pretty much twist and writhe. So you see this kind of twisting and writhing, if applicable. And then the mutual helicity you don't see. It's just the fact that you have non-potential current-carrying flux tubes tightly packed and interacting with each other. But the elephant in the room here is the mutual helicity, so much bigger than self-helicity. And what we see around strong polarity inversion lines is that you have a closely following temporal profile of the self-helicity with a mutual helicity, but they are shifted in time by a few hours. So if you take the gray curve and you move it ahead in time by a few hours, you're going to be matching the mutual helicity time profile. So what we think happens, and this is what causes the irreversible situation, is that you have magnetic reconnection, you have resistive processes along the polarity inversion line always happening. And this progressively gives you a more twisted structure. This has been seen in some pretty dramatic cases. Again, the Spiros Patourakos showed on the left a situation in which you had a confined flare giving rise to something like a hot flux drop before the eruption, and the eruption came a few hours later. And then another example by Georgoulis and company, in which, again, in a very strong dynamic active region, 11.4 to 7 or 6, I think, you had this kind of situation. You see a hot channel, you see the flux rope. These are major examples. What we saw with helicity is this little chipping of magnetic reconnection and energy loss that always happens along polarity inversion lines and gives rise to more twisted structures than before. Okay, so yeah, we have all this. What we think happens is that you have the nominal evolution in the active region. The majority of active regions are going to be, giving you some flux, polarity inversion line formation, not very strong perhaps, and then full flux evolution and decay of the active region. But in some cases, you may end up with strong polarity inversion lines. Animation didn't show very well, apologies for that. You have some broken symmetry right over there. You have some net currents happening, and these net currents are non-neutralized. They are raw currents injected into the corona, and this gives rise to a Lorentz force. The Lorentz force is going to be creating the shear, we believe, or we think, in which case you have all the other effects I talked about, and you have at least one eruption. If the active region, if the configuration has more to give, then you get around this loop until you end with whatever helicity you have to shade away because of the helicity conservation principle, and then you get into the nominal evolution of decay in there. So the Lorentz force here that is caused by the raw currents along the polarity inversion line seems to be playing a significant role in our mind at least. So in essence, the emergence of strong polarity inversion lines, and by strong we mean polarity inversion lines with magnetic fields already above the equipartition value right there on the photosphere, so that the magnetic forces are strong enough to move the plasma, is what we think separates strong polarity inversion lines by weak polarity inversion lines. And it's pretty quantitative. You can do that. So again, the Lorentz force and its role, it's far from being confirmed. It is in my mind at least, but it's good. There are different opinions. It's good to try to see whether it works or not. Either a positive or a negative result out of that is going to be a good, a meaningful conclusion because it moves ahead. But Lorentz force on the photosphere is a notoriously difficult quantity to get. So what happens if the Lorentz force is confirmed, if we manage to do it? This is going to be the smoking gun. The smoking gun that we are looking into the pre-eruption situation. Strong polarity inversion line, Lorentz force, shear, and then you end up with at least one eruption or with a sequence of eruptions if the polarity inversion line is strong enough. This is going to be confirmation. If not confirming, then we're going to have to make sense again of the MHD equation of motion, because in strong fields, it is the Lorentz force that is the dominant situation, so it has to have a relation with the peculiar shearing motions that you see along the polarity inversion line. Okay, so concluding remarks here, we have moved, I think, beyond the debate of a sheared arcade versus a flux rope, reasonably so. So this is a new era, but as you have seen, more burning questions remain, and this came out by the previous talks as well. I think that we should be looking into the Lorentz force, helicity is there, and we should be looking also into new tools that will allow us to have ultra-fast and routine calculations of non-force-free fields all the way down to the photosphere, so that we evaluate the role of the Lorentz force in the low chromosphere and slightly above. So all in all, just to finish, it has been a wild ride. It has been a mess over the past 20 years. You have different pieces of the puzzle, but we are making progress, I have to say. Dave Rust, 30 years ago, had all figured it out. It's the helicity, stupid. He told us since 1993, right? Then, in one of the countless discussions and debates about that, I was close to Spiro when he said, I get it now, everything is a flux rope. No, well, not everything, but close enough. You get there in the course of time, okay? So just by finishing, I would like to really thank Spiro for what you have taught us all these years. It's been a privilege to be interacting with you and communicating and debating with you. Thanks a lot.
Manolis, I would like to make it a little bit more complex. Unfortunately, I wish I could make it simpler, but it's going to be a little bit more complicated. I think if you want to do the Lorentz force, you have to include the subphotospheric region because it's in flux emergence that you see really the role of the Lorentz force of the emerging flux rope to give you the sheared arcade. And in fact, I would say that, you know, if we can go to simulations where we include the convection region, then we can do fully self-consistent models, and then we can settle the issue as how much shear there's actually there, how much twist actually arises, and so on and so forth, rather than by putting it in by our boundary conditions or our initial conditions. So we're going to have to go below the photosphere.
Yeah, I agree with you. That's a good point.
Comment on that, Spiro. I mean, what you're doing in that regime paradigm is replacing your made-up boundary conditions with a made-up initial condition. So you think back to Hugh Hudson's famous cartoon, right? J equals 0, underneath the photosphere, J equals whatever you like. You've kind of got an infinite parameter space to play with, so it is the way to go, but it's less constrained somewhat.
I can put in, as an initial state, a flux rope in the Coronal, no problem, right? I can put it in, or I can put in a bunch of shear, I can put shear and twist and whatever I want to do. But is it true that you can pick a flux rope from below the surface that's going to give you automatically a twisted flux rope above in the Corona? You don't know. Yeah, so my feeling is that if you start with below the surface structure, what happens in the Corona will evolve, will appear self-consistently rather than by assumption.
Well, there have attempts. There have been some local attempts, active region scale attempts to see what is happening below the photosphere, and these might prove useful. But again, the big challenge here is to make sense between what you think happens below the photosphere and the photospheric evolution that you see. So it's really data-driven, and you have the photosphere. You know, it's kind of a double-edged sword in the sense that you know that eruptions do not start there, but it's the most quantitative information that you get about what is happening a couple of megameters above. So you have to be careful, but at the same time, you have to rely on this.
Manolis, I want to be sure I understand your very intriguing result that alpha decreases before the eruption, then suddenly increases at the eruption. So this implies that those measurements of alpha are being made in a high beta environment, highly non-force-free environment. Is that what you're saying?
Yes. So this alpha calculation is based on a method that Yang Liu has to mask the area of the polarity inversion line. So we're talking about strong magnetic fields, very sheared magnetic fields, and then we had the flux-weighted alpha value along among this area over there, and we showed its evolution before and after the eruption.
But it's kind of strange that this observations, it has to be high beta situation where the
It's not high beta because, I mean, you know that in strong polarity inversion lines, you have beta already smaller than 1 at the photosphere.
Right, so I am very confused now because alpha correlates with free energy.
Sure.
So you're saying that before the eruption, the free energy is going down. The eruption causes the free energy to go up.
It's not the free energy that goes down, I think. If you had the 3-dimensional configuration there, you would see the energy doing whatever, but it's probably not an artifact, but a consequence of the evolution on the photosphere because we are restricted on the photosphere. So what we probably see, I mean, Hugh Hudson talked about the implosion picture, and George Fisher as well, in which case you have magnetic fields becoming more horizontal after the eruption. Well, before the eruption, if this is valid, what we see is that the situation probably bubbles. I mean, the configuration probably bubbles up and the magnetic field becomes more vertical. So you do not have that strong of a signal to get the alpha value, to get a strong alpha value on the photosphere. And then you get that after the implosion. Well,
yeah,
can discuss about that, yes.
About your comment about Lorentz force. If data-driven at the surface, don't you need to worry about gravity? Because that's really the interface between gravity-confined photosphere to Coronal, which is probably ignored. But
That's right.
Right.
So,
how big is the gravity play a role in your
right.
Lorentz force? Yeah.
You do have, obviously, you do have the gravity term in the MHD equation of motion, which I didn't show. But what you count here is the beta parameter. I mean, you can do it a couple of ways on the photosphere. If you see what is the beta parameter on the photosphere, and you calculate the equipartition value, the value of the magnetic field that you get a beta equals to 1, then you come up with between 1 and 1.5 kilogauss. At delta sunspots, we have field strengths of the order 2 kilogauss and more, which makes the magnetic field, the beta parameter, the magnetic field energy density, and the magnetic forces in the MHD equation of motion the dominant factor. It is there, but it's not as important in these situations, we believe. Yeah.
Thank you very much. Thank you very much, Manolis, and for the other speakers of this morning. I think we have coffee break now, and we reconvene at 11.
last night. It looks like it. All right, everyone, please take your seats. Andre, how you doing? All right, welcome back. I hope you enjoyed your coffee. I understand we have 30 remote viewers, actually, and they can't hear us very well. So please, 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 either use the handheld mic if you roam around, or if you use the podium mic, stay at the podium and make sure that the mic is close to your mouth, because they apparently can't hear us very well. So now Sophie Masson is going to chair this session.
Jim. Okay, so we're going to start the next session, and we're going to start with Sarah Gibson, who is going to talk about Slinkies. Okay.
Okay, thank you so much. It's my pleasure to be here. The title of the Sparrow said, I kind of remembered conversation/discussion from about 20 years ago, and we were talking about magnetic flux ropes, and he says, yeah, magnetic flux ropes, show me this Slinky, okay, in the observations. And the point which I'm kind of going to make today is that you don't actually usually see a Slinky like you do in these representations of the magnetic field lines. I can advance. Can you advance for me, Calvin? There you go. And in fact, when you look at what a magnetic flux rope looks like throughout the corona, it doesn't look that much like a Slinky. Every single image that's shown here has been described in terms of a magnetic flux rope. And today I'm going to be talking about that, and I'm going to be talking about the magnetic flux rope sort of in its life sequence from emergence through the photosphere, existence quiescently in the corona, and then, of course, eruption into the solar wind. I'll be talking about models and observations and how they match, doing the forward modeling to try to make the connections. And this is kind of a sneak preview of some of those. All right, before I get started, though, I think we need a definition. What is a magnetic flux rope anyway? Because it can mean more than one thing. It can be that kind of classic Slinky-type structure winding around an axis, or something more complicated even, like a spheromac. And I'll get to that in just a sec. So that is my definition, that you have magnetic flux wrapping around a central axis, or axes in the case of a spheromac, leading to topologically distinct magnetic subsystems which have observational implications, as I'll describe. So here's the classic single-axis flux rope, much like Yuhong was showing. You're seeing magnetic field lines in the different colors, and you're seeing a cross-section when it kind of lines up with your observing viewing point there, with the dots showing the magnetic flux surfaces, which mean basically regions where the magnetic field line is lying along it and cannot cross through it. The brown dots at the bottom are showing you where the dips are in this magnetic structure. And it's interesting, when you start looking at fairly large magnetic flux ropes in the sun, you really have to think about the curvature of the solar surface as well. And the point I want to make, and I'll come back to, is that all these brown dots, these dips, lie well below the axis, which is represented by that black dot in the middle. Okay, here is what's called a tethered spheromac. Now for the moment, look at the one on the right, which is an analytic model. And what this means is that there are two axes of rotation. There is the red ring, which is going around the donut hole or apple core of the spheromac. And then you can see the gray line, which is actually the other axes. And the point is that actually most of the magnetic field lines in this magnetic structure are wrapping around both axes. On the left, and I'll come back to this later, is a numerical simulation of something which is topologically equivalent to the structure on the right, the analytic structure, and something that is created by starting out with a single axis flux rope on the left that then reconnects during eruption and creates this tethered spheromac. Why should we care about magnetic flux ropes besides the fact that they're super cool? Because they do erupt, and Yuhong has already shown us that. They represent a nice demonstration of a universal property process of magnetic energy storage and release, because a magnetic flux rope has built within it, it has a hoop force that wants to expand outwards and upwards and out and away in an eruption. But there's a strapping force from the potential field, in this particular case, the red field lines that overlie it, but also built inside that magnetic flux rope, there's some restraint as well. So magnetic flux ropes are interesting because they have been demonstrated to erupt. They don't even need, oh, dare I say it, they don't even need reconnection. It's been shown that ideal instabilities such as the kink or the torus instability can drive it. In this case, Spiro, answering your question, there is reconnection because reconnection tends to happen. And in fact, you end up with reconnection acting as an enabling factor in a tether cutting fashion to put that axis higher and higher to the point where it may be unstable to the torus instability. All right, what would we expect this flux rope to look like as it emerges through the photosphere? Well, one of the first things people looked for were U-loops. The telltale signature would be the vector magnetic field at the photosphere with a strong alignment at tangent at the polarity inversion line, as well as a concave up field geometry. And we've known since the 90s, I think it was, when Katie Lecca showed us that magnetic field emerges with twisted magnetic fields. And so this kind of organized emergence was something that people looked for, and in fact found in vector magnetograms, as in the references shown on this slide. And coming back to the spheromac for a moment, in the case of an emerging delta sunspot, Leitz and colleagues were able to reproduce the time evolution of the vector magnetic field in a manner that was well modeled by the emergence of a closed magnetic structure like a spheromac. But wait, and I know I can see the smoke coming out of Spiro's ears at this point. Can a flux rope really emerge? This kind of smooth, just moving it past the surface, you know, that's cheating, isn't it? And yes, it is, up to a point. Because what numerical simulations that have looked at the emergence of magnetic structures through the photosphere have shown is that it is not a smooth process. There's fragmentation. Mass, it's heavy, it stops that upward expansion. You end up with reconnection, and during the emergence, you end up with a partial emergence. And you can, in fact, end up with a new flux rope axis forming above the surface as part of this very messy, fragmented emergence process. And here is the answer to your question, Spiro. You were saying we should have models that show the emergence of something that's actually fully subphotospheric through the photosphere in a realistic way. On the right, you're looking at EUV emission from a flux rope. This is one of Yuhong's flux ropes in a convective interior simulation that is going from the interior of the sun, buoyantly rising into the corona and using Matthias's Muram code to model what happens as it crosses that boundary. And it does not smoothly cross that dense solar, from the dense interior into the corona. It is radically fragmented in the process of that emergence. And yet, the magnetic flux rope has reformed and is stable. It may not be the same magnetic flux rope. It's had a serious identity crisis, I'm sure, in the courses of this whole process. But a magnetic flux rope has emerged, has reformed, and indeed has been shown to be stable for a time before it, in fact, eventually erupts. And so this makes sense, and this is something that Dave Rust used to say, that the magnetic flux rope is the building block, is a building block of the coronal atmosphere, because it represents a minimum energy state for a given amount of magnetic helicity or twist. And this also comes back to what we heard from Manolis in the last talk. So whether it's a smooth or a bumpy ride, the end result may be the same, a temporarily stable flux rope suspended in the solar atmosphere. All right, so let's talk about other observational indicators. The prominence. And I actually already showed you a flux rope where I painted the dips. I think this is something Guillaume Alonier did the first time, taking that magnetic skeleton of the magnetic field lines and looking where the field lines are concave up. And basically, in spherical geometry, looking at where you have an opposing force to gravity. And what's interesting about this, and I'm showing you on the left an actual observation. Let's see if I can get this to work. Try it again. There it is. Here's the observation. Here's a classic single axis flux rope where the dips have been painted. Here's that one that Lights et al. Used in the, which is actually a little Spiramac. And what I'm going to point out is this looks an awful lot like this and this, in that it is a sheet-like structure above the neutral line. Even with that complicated Spiramac magnetic topology, you end up with that same kind of sheet-like structure above the neutral line. And that's because the axis with the dips is the one that it's gathering along. But of course, again, that was an idealized picture, painting the dips. Yuhong has already shown us the state of the art in terms of what a prominence would look like in the context of a magnetic flux rope when you really take into consideration the condensation processes. And this is something which has been shown also by Sean Keppens and colleagues over the last few years, that you end up with the prominence material indeed gathering in those dips, but other structures become clear, including the coronal cavity, which surrounds the prominence. And the thing about the prominence is, no matter what your model is, if, well, step back, in the context of the magnetic flux rope model, the prominence is only showing you a tiny piece of that magnetic structure. The coronal cavity that surrounds it is actually a better indicator of the volume of the magnetic structure that is holding the energy. But before I get back to cavities, let me talk a little bit more about prominences or filaments as observed on the disk, and sigmoids. And sigmoids are S-shaped or backward S-shaped structures that can be seen. Filaments can have that kind of a shape, but also in soft X-ray. And what I'm showing here is an inverse image in soft X-ray, so dark is where you have the bright loops, that has this backwards S shape. Here is the H-alpha filament that goes along with it. What's interesting is that when you have the filament and the sigmoid together, they both have the same directionality of S. And what does that mean, and why is that significant? Well, we've already talked about how the dips in a magnetic flux rope might give you a structure aligned with the axis and give you something which is basically sigmoidal in the filament. So what is what is the sigmoid showing you? In a magnetic flux rope, you get both backwards and forwards S's. The backwards S's are on the bottom, the forwards S's are on the top. The implication that the sigmoid in X-rays and filaments are in the same direction is that both structures are showing you something about the bottom of this magnetic flux rope, if that is the model you're using. And we have a reason for why the bottom part of the flux rope would be lit up. Thank you. Because the bald patch separatrix surface, and I mentioned earlier the topologically distinct regions, it's been demonstrated that current sheets form at the bald patch separatrix surface, which is the interface of right where the flux rope grazes the photosphere. And you can get interchange reconnections there because of this, and you can go from J-type arcade field lines to S-type, and essentially in a form of tether cutting, continue to feed this flux rope and make it rise higher, as I described below. I will comment that the quasi-separatrix layer is the generalization of the very topologically pure bald patch separatrix surface, but the concept is very similar. All right, let me get to cavities, prominence cavities. And as Yuhong showed, prominence cavities are observed in white light, they're observed in radio, they're observed in various wavelengths of light, and they have substructures that are quite interesting. So let me show you here, for example. This is, again, an inverse image in soft X-ray. There you've got the prominence. Notice it's lying below the center of the cavity. The center of the cavity has this hot, chewy nougat, as Hugh Hudson called it. I think of it as the lollipop on top of the stick, which is a hot core. And you see structure in EUV. You see these kind of horns that Yuhong talked about, again, above the prominence. And you see swirling motions. And when you have a magnetic flux rope model, you have a reason for this kind of circular substructure in the form of the magnetic flux surfaces, which are shown again here. Because the magnetic flux surfaces is where you have these distinct features forming. And in terms of, we even see rings. We see nested line-of-sight flows with the comp and the UComp observation, which are associated with these substructures inside the cavity. As the structure starts to erupt, and again, Yuhong showed you a simulation, a more recent simulation that shows this, but here's an example of an observation of a cavity with that substructure, the filament lying below it, like the lollipop stick, and the horns. And all of this is happening because, in this context of this flux rate model, because the underlying magnetic structure is the one that has the field lines that the plasma can move along and give you this kind of concentric ring behavior. On the left, on the right, I have a movie of the magnetic flux rope where the field lines are color-coded by temperature, where the hot ones you can see are in the middle, consistent with the hot core or chewing nougat. Down below, you have a current sheen forming. That's where the reconnections are happening, and the thing is starting to tether cut and start to move upwards. It's also where the prominence lies in the simulation. Now to the least controversial slide on the whole one, with the blessing of our great leader here, Antiochus et al., which is the concept of the flux rope, or plasmoid, if you'd rather call it that, in the eruption is one that is more or less universally accepted. Whether you start from a sheared arcade or a flux rope, as it erupts outward, it is something which is somehow disconnected in this plasmoid type way. But the question, of course, is what happens before that? And if you have this evidence of the magnetic flux rope, in this case, this is one which was around for 2 days before it finally erupted, with all this substructure, and slowly, slowly, it starts to tear up, and it starts to show that current sheet below, and you get these reconnections, and it erupts, it's quite consistent with the model of a pre-existing flux rope. So I know I'm running out of time. I'll just mention that one of the things that have also been argued for the presence of a flux rope before an eruption is a sigmoid transitioning to a cusp-like topology, so going more to potential. But in addition, many, many cases exist where a sigmoid, a soft X-ray sigmoid exists that does not transition to a simple potential arcade, but to something more complicated, which has an arcade, but below that arcade, there is another sigmoid. And this is something that we find in simulations, that eruptions don't always, of a magnetic flux rope, don't always completely leave the building. They have partial eruptions with reconnection inside, so that part of it leaves and part stays behind to form the core of a new flux rope that grows and rises. And when that happens, this, coming back to what I showed at the beginning, that numerical model where a spheromac formed during eruption, if your pre-existing structure is a magnetic flux rope, then during the eruption, you don't go from sheared arcade to flux rope. You can go from flux rope to something like a tethered spheromac. And indeed, this is interesting because observations in the solar wind show bidirectional streaming of electrons, which are consistent with an attached kind of arcadal line, but they also show unidirectional streaming, which is consistent with basically an open field line, and they show flux dropouts. And this is consistent with something which basically doesn't connect to the sun at all. And when you have this kind of tethered spheromac topology, you expect all three. And I just wanted to say, when I started writing this talk, yeah, so there was a lot more evidence that I could have talked about, and I didn't. So the conclusion is, first of all, it doesn't look like a Slinky. Maybe that the granddaddy Prominence is the one example we have, but in general, the CME and its precursors don't look like Slinkies. They look like whatever stage emergence they are and whatever you happen to be observing, whatever piece of that plasma you're observing in your observable. And the simple Slinky-like magnetic flux rope cartoon is actually too restrictive. There can be more complex topologies, for example, tethered spheromac, and you need to think about these transitions and evolving states from sheared arcade to flux rope, as Manolis was describing, and flux rope to tethered spheromac. I do firmly believe that in the sun, not every eruption in a CME is coming from a pre-existing flux rope. I think that's simply impossible, because it's a question of whether it has time to reach that metastable state before something happens to do with how it's driven from below, or what the topology, including the breakout topology, is above, as to whether it'll erupt well before it forms a flux rope. But in the case of these quiescent filaments and these ones with cavities, I think we have strong evidence that the flux rope is there before eruption. And I just want to comment that we have ways of looking at the flux ropes we've never considered before. Punch is going to look at polarization ratio in the erupting white light CME out into the heliosphere, and we can look at the chirality of the structure. Cosmo and Phaser can probe the magnetic fields. I didn't even show you my lagomorphs, my favorite flux rope evidence from the linear polarization of comp. But if we have bigger telescopes that allow us, like Cosmo, to look at the Stokes V, we have a strong indicator of what I think is a real observational distinguisher in the precursor structure, which is whether the energy in the shear is stored well above the prominence, or is it in the prominence? And that might be a way to really distinguish between these precursor sheared arcade and flux rope models. And finally, I'm never going to convince Spiro. I mean, you know, I'm not even going to try. I think for Spiro, he needs something that he can see and he can even touch. So Spiro, I have a present for you. All right, so here's the present. And you'll be glad to know I brought them for the whole class as well. I have 60 here, so hopefully it'll be enough. So take one and pass it along, and thank you. Now you want to see ruined, you should open to a Spheromac. I've destroyed Slinkies. But.
Thank you, Sarah. Yes, we can. So questions, sorry.
So it's going to be dead easy to convince me. If I look at the corona in 2 or 3 million degrees, I see what a bunch of loops. Some of the loops look like McDonald's arches, some are sheared loops, but I never see a magnetic field line that has this kind of up and down and twirly-twirlies of your Spheromac, and I never see a magnetic field line that looks like this in 2 or 3 million degrees. And the question is, why Spheromac? And put in some coronal heating, you know, some uniform heating, for example, you're going to see right away those field lines.
So take a look at the actual field lines in the flux rope, okay? These are the ones that Yuhong's showing. And notice that on the left, and in her simulations, she's showing you what you see in EUV, okay? And what you're going to see is not that full Slinky-like structure. What you're going to see are ring-like structures, which we do, and you're going to, when it's lined up just right, and what you're going to see is sheared sigmoid-type structures when you're looking down on them. And what you're going to see is the prominence as well. But you're not going to see, I mean, there's no reason, in fact, if you look at this, you'll see that many of the field lines have, the temperature varies along them, the condensation is at the center of them, and parts of the field line are at coronal temperatures and parts are cool. So you're not going to see that as a single continuous field line.
But if you were to take that structure and put in 5 million degree plasma, especially put it, you know, in various locations so you get what looks like an active region where you have all these coronal loops, I would say you will see that wrapping around. I don't see how you would not see it.
Well, here, this is an example, the one from the Miram. See if I can show it. You have to go back a few to make the movie run. And again, you know, there is, on the left, I've got the field lines with the flux rope. Do you see it? I don't see it. It's dynamic. You're seeing parts of that magnetic structure, but you're never seeing all of the magnetic structure at any one time. You're seeing different field lines lit up in different ways, and sometimes not even lit up. Sometimes you're seeing condensation. Sometimes you're seeing flows. Well, why would you expect to? I mean, none of the simulations give something that looks like that.
Stop the evolution at some point, and then start putting in heating on those field lines.
They all have heating on them. So. These are all heated.
Right away. But anyways, this is an argument.
I'm never going to convince Spiro.
Let me just say, Sarah, this is really important work, and we just need to continue. That's all it is.
Absolutely.
And we need better observations, as you pointed out. Yeah.
Okay, we have time for one more question. Jim, do you want to take it?
Okay. Before my question, let me first say, some people approached me before the meeting and said, boy, I'd like to, it's not appropriate. Loves a debate. He would be disappointed if you didn't bring up those things. But here's my quick comment related to the synthetic observations. In the ones that Yuhong showed, the first set of simulations, I mean, very beautiful, and they include some really nice physics that a lot of codes don't include, like field line thermal conduction and radiation. And I think it's very meaningful to compare those synthetic images with real observations. But I'm a little bit concerned about something. If I understood correctly, in those simulations, the lower boundary had a temperature of about 500,000 degrees. So there really isn't a transition region in chromosphere. And so the very, very important coupling between the lower atmosphere and the corona that gives rise to things like evaporation, I think that's not included. So it'll be interesting to see how the synthetic observations change when that aspect of the problem is included. And I think there could be some substantial changes.
And this is something maybe Yuhong can answer, but the simulation that's showing right now, it includes all that, does it not? It has the full chromosphere transition region. But, and then the other ones that Yuhong was showing earlier include
simplified low boundary with a transition temperature, but with a kind of a pressure adjustment to allow for evaporation. If you have downward thermal conduction, it will increase the pressure to sort of really roughly mimic. But I agree with you, it's very idealized. But there is transition region in the field lines. There's local, each field line is a atmosphere containing the chromosphere temperature transition up to, I mean, that part is in there. It's a little, you know, there's a transition region, prominence coronal transition region along the field line being established. That's the horn, actually. So it's just a general comment. But it is idealized, agree with you.
In a really rigorous way, you need to include the lower atmosphere and this very important both energetic and dynamic coupling between the corona and the lower atmosphere. Yeah, but it's tough to do, so I applaud the simulations. I mean,
I think we're going to move on, so. Well, there was plenty of time for at lunch break. Okay, sorry, we just were running late. Okay, so thank you, Sarah, again. And the next speaker is Peter Wyper, and he's going to present some works on CMEs in pseudostreamer context.
Yes.
Thanks.
Hi. Hello, everyone. Hi, Spiro. So yeah, this is kind of my sort of most recent work, but I thought, given that it's Spiro Fest and so on, it might actually be nice to sort of give the history as to where the ideas that have led to this work came from. We're going to start with Jet. The story, I guess, we have to go back to the early days of my MPP. So I came to Goddard in 2015, having only ever studied 3D reconnection. I didn't do eruptions or jets or anything along these lines. And when I got here, my kind of task to learn ARMS, so I needed some sort of thing to try and do that. And so the thing we used was extending Etienne and Spiro's lovely jet model, which we're going to hear more about in the next, tomorrow, to kind of close configurations. See if I can make this work. Ooh. Oh yeah, close configurations like this. And we got a nice couple of papers out of it in 2016. But the first time I presented it was actually in 2015, and that was at a conference where Ron and Alphonse were making a big splash with their Nature paper on sort of mini filament coronal jets, and how these sort of tiny, here we go, tiny little jet-like, tiny little dark structures are erupting out, which they called mini filaments, building on previous work by Noor and so on. And actually afterwards, Ron came up to me and was like, your model doesn't have a filament. You need to fix that. I was like, okay, fair enough. So never one to turn down a challenge. I went, okay, let's go back to the drawing board. So I started looking at the sort of standard embedded bipole topology that we've already heard Judy talk about in a sort of open field configuration. And I was trying to think, how can I get a filament into here? So I just started adding shear in the sort of standard way we do, but I made everything too symmetric. So I put a load of shear in very close to polarity inversion line, and it kinked and it writhed and it did all sorts of things, but it didn't give me a jet. And at the time I didn't know that well enough about eruptions. And one day Spiro was kind of wandering around as he does, kind of just popping in on the students, seeing what they're up to. And of course he wanders in and goes, Wyper, my good man. Topology is basically a quadrupole. Breakout will solve all your problems, because of course he did, right? and he was right in a sense, right? So, you know, Breakout, he's like, well, you know, what you really need to do is you need to get that overlying flux out the way. So my I had a sort of filament on one side. It's like, well, if you can make it sort of asymmetric, it'll move it all over to one side. You'll get a jet, right? So I then wandered off to go and tell another student how they were doing their research wrong too, and left me to figure it out. And that led then to this sort of Breakout 2, Breakout Harder, the sequel, jet model, which we then sort of pushed for many years in following that. So basically the idea being, if you're not familiar, that because of the asymmetry now, I've put a filament on one side. It can lead to some breakout reconnection because of the sort of asymmetric expansion. And that breakout reconnection can sort of slowly remove that overlying flux, the problematic overlying flux I'd had before. And it would allow the sort of flux rope, which eventually forms, to rise and eventually reach the open-closed boundary, transfer its twist, launching a jet. So in some senses, it's very similar to the original breakout concept, and that you've got this feedback between the breakout and the sort of rise of the flux rope. But in other ways, it's quite different, because there's not a lot of ideal expansion of the flux rope. We're in a very confined situation here with sort of a uniform background field. And the other key difference is that the real explosive behavior only happens when that flux rope reaches the open-closed boundary and it gets reconnected, or one leg of the flux rope opens up. Okay, so that's the kind of key differences. And some nice follow-up work by Pankaj Kumar and Judy sort of confirmed that this sort of generally seems to work really well for jets. Okay. Now, the reason me and Spiro got on quite well is because we both think in terms of topology. So this is a slide I presented at AGU in 2018, where I went, right, what are the different breakout configurations effectively you could get, and let's work through our different options. So along the top, you have the kind of jet that I've just described. And bear in mind that this is kind of slightly independent of, is it a sheared arcade, is it a flux rope, is it not? We're mainly talking about once it's off and running, how do you get that overlying flux out of the way? So it can work for both. They're not mutually exclusive in any way. You got then a sort of a second row here for sort of a confined sort of flare or confined jet. And depending on what the sort of next stages are, you might get sort of secondary eruption. We've got the classic breakout down the bottom. And then I kind of drew a few cartoons for assuming it was some sort of jet-like CME for the pseudostreamer. And it turned out that that's actually a bit more complicated. The strong as cartoons are, we need our simulations, right? So let's move to sort of what the observations are telling us. So I sort of like, well, it's basically the same topology as an embedded bipole. Okay, sometimes it's a bit stretched, there's sometimes multiple nulls, fine. But nonetheless, you'd sort of expect it would look like a jet. And in some cases, it does. So here's a nice, simple example. Sort of white light running difference from Wang et al. There's a small little flux rope erupts up, hits the open-closed boundary, transfers its twist, drives a jet, right? The kind of CMEs you get from these kind of events, very narrow, very unstructured, basically jets, just on a bigger scale. Great. And I did some later simulation work that was in one of these more complex multiple null configurations that Judy kind of hinted at earlier. And it does, in fact, have a very low corona behavior that looks exactly like that. So it's just the same as the previous jet calculation I showed, but now, that's obviously the sun, it's a lot bigger. Now in that case, there's interaction with the helmet streamer, at least to more complex dynamics. I won't go into that, but assuming it doesn't clatter or sympathetically erupt something else, you're gonna get something very jet-like. Okay, so far, so good. But what about these kind of events? So these are also sort of pseudostreamers. This is a large scale anemone region. This is some nice work by Pankaj again. This is running difference in AIA. And what we've got here is the dome is here, and you're going to see sort of some sort of loop starting to open up, and then suddenly a large, huge CME-like eruption, right? Same topology, very different behavior. And the CMEs they produce, massive, right? These are not narrow, unstructured jet-like things. These are big and ugly and drive a big shock. And behind them, actually, I should point out, there's some sort of radial striation kind of features as well, which I want to get back to towards the end. And my question with myself was, okay, fine, I've kind of managed to do the jet-like ones. What do I need to do to get this kind of behavior? Breakout 3, breakout with a vengeance. Supersize the jet model. That's all you need to do, right? Make it a hell of a lot bigger. And the main changes now are that we have moved it to spherical geometry. we have a radially expanding background field, and we have the exact same bipole, exact same field strength ratios and everything else, but it's now relatively big relative to that background field strength drop-off. So if you form a flux rope, it's going to want to ideally expand a lot more than the previous cases did in the Cartesian, whatever. So I'm still driving it the same way. I'm doing slow rotational driving, forming the flux rope, and so on. Okay, so what do we get? Let's have a look. So we form our flux rope, everything's expanding out, breakout reconnection kicks in, starts going bananas, and then we get this massive old CME-like eruption. So now the fast reconnection is happening well before our flux rope is kind of disconnected or anything like that. So it's essentially in this phase here, there's a fast flare reconnection, this thing's massively expanded out. If you were to look at that low down, it looks like a typical CME, like typical flux rope eruption, CSKP, all the sort of typical things you might think. But it's still in the jet topology. It's still surrounded by open flux. So eventually it can't stay like this, even if it may start out like an eruption. Oh, but I should say, if we compare it to Pankash's thing, this was just a really fortuitous timing, so I wanted to put these movies adjacent to each other. Check out the sort of in-phase eruption they both do. So here we go. Whee! So we catch that lovely rolling motion, right, as the flux rope's deflected towards the null point, as kind of lots of other previous work has shown too. But they're kind of new physics that, like the other previous work was much more localized, so like Tibor toric stuff, Ben's stuff, is all more localized, didn't have this extended domain, all the wind and everything else that this now does, is that we can follow what happens next. And what happens next is you get this big disconnection on the leg of the erupting flux rope structure. And that's just very simple, right? Because basically your flux rope is stretching out, and one of those legs is going to have to be facing the other way, the magnetic field direction, from the surroundings, right? So that will ultimately lead to interchange reconnection, it will chew through it, and it will lead to a disconnection. So in terms of the topology of the system, thank you, it's exactly the same as a jet. All right, we've got the opening up of one of the legs of the flux rope and the transfer of twist, but it's presenting as a large-scale CME. So we can unify our thinking of how this works in terms of sort of the magnetic field evolution, but the morphology is very different. And we can sort of look at the sort of CME itself as well. Ben kind of hinted at some of this with these really nice synthetic observations. I haven't put too much of them in. But here's sort of density in a cut. And you see this little cavity there. And that cavity is a sort of signature of that embedded flux rope. But at this point in the evolution, it's disconnected. So it might look like it's still connected on the surface, but it's not. The other thing to point out is that this is the in-plane component of the flow, or sorry, into the board, I guess. And we have a sort of rotation, right? We've got red on one side, blue on the other. So this thing is rotating, again, in a similar way to large-scale jets. Now, in terms of the internal CME structure, then, it's quite a big, messy thing. We've got blue here is the original CME flux rope, which you can see kind of connects down still on 1 foot point. But then actually in behind it, kind of in the sort of tail end, there's lots of these other flux ropes too. And they are quite likely what's creating those radial striating structures that I mentioned previously in the chronograph. And where do they come from? Well, the original flux rope, of course, we've created by, the sort of typical flare-like reconnection and everything else. These later ones, these are actually due to plasmoids and in the interchange reconnection process. Because there's a very large current sheet gets formed as this disconnection happens. So you get lots of large plasmoids, as Ben was mentioning in 2.5D. In 3D, what they create are these twisted flux tubes that kind of follow in behind. And these are things I've seen for, actually depressingly a decade now, since my early postdoc days. So here's a null point simulation I did, where I sort of took a regular old null and 3D null, stretched it until it went tearing unstable, and we carried all these flux ropes. And then once I was at Goddard and I was working with Rick, I sort of generalized that idea to what happens if the twist gets shot out as part of coronal jets. Now, and anecdotally, when I first got to Goddard, this was my most new work, and I was super excited about it. So I remember showing Spiro this in his office. And I was like, I've discovered this thing, and I've moved it apart, and I've got loads of reconnection. And he went, Yes. And he walked up to the board, and he drew this picture. And this is the dangerous thing with Spiro. Because although you may have just discovered something or really been deeply thinking about something for maybe the last 6 months, he'll probably have been thinking about it for the last 15 to 20 years. And just because the simulations have just caught up to you, doesn't mean he hasn't already figured out what it's likely to do. And for context, this is me back in 1996. So a little bit before I got into solar physics. All right, so we've now we've built up this big picture, and we have like lower expansion events, higher expansion events. One looks like a jet, one looks like more like a CME, sorry, and there's a disconnection and so on. So we're unifying the picture, and that's kind of what I like to do if I can. So in summary, breakout concept, incredibly versatile. And if you combine that with topology of the system and the surroundings, you've got this really powerful tool for figuring out how different kinds of eruptions with very different morphologies can kind of generally be understood under the same umbrella. And I should say these ideas are all fantastic, but a shout out should go to Rick DeVore at this point, because we would not have the ability to test them and demonstrate them had it not been for the amazing ARMS code. So that's it. We've had the ARMS workshop this week, and we've been sort of saying thank you very much, Rick, and so it's another opportunity to say that here. Open questions, lots of things still to be done. What sets that transition from jet-like to CME like, for one, but there's so many others that we're already discussing, right? So the work doesn't stop now. And so I thought I'd finish with my favorite Spiroism, which I've heard many a time. So when you're midway through trying to convince Spiro of something, particularly when you slightly disagree with them, you'll hear this phrase, so what you're really saying is this, which translates to, let me tell you how what you're explaining is actually really what I've been saying the whole time. Beware when hearing such a phrase. So thank you very much.
Thank you, Peter. Questions? Nope. Okay.
Spiro. Oh, very nice, thank you. One way is that with a jet, the mini filament fluctuate will erupt, and the whole thing will be eaten up in that that interchange breakout reconnection, and so it opens up and goes onto to the open field.
Yes.
And then the plasma can go out and everything as a jet-like thing. And then if there's so much flux in the fluctuate that it can still survive that, then it really is a CME. And so they're boundary ones, and then your last case, I think, might be a different case. But anyway, that's one way that, at least I think of it.
Well, exactly. Well, I mean, that's the thing. You're very right that what you observe looks very different. And the sort of behavior of them is different. The energy release timings are different. So, like, I'm not saying they're exactly the same. What I am saying is they ultimately follow the same route. Like, you have to still open that flux. You still have to do that.
Yes, exactly. I think that's a good.
But understanding this is crucial now. Now we have our in situ measurements, things flying through all this stuff, as Ben was demonstrating with these really nice synthetic stuff. So we need to understand this. We need to get away from essentially things like knowing that pseudostreamers, when you see something erupting from them, things are not connected at both ends. I think we can kind of rule that out, because I've energized this thing hugely, probably much more so than a regular pseudostreamer would have, to make the point that even if you really hit it with a ton of free energy, it's still going to open up. So that's kind of, this is what I'm trying to aim for.
One last quick comment, if I can. We've also seen some cases where there are these large eruptions in the really large jet-like, jet-like topology, but with large fluctuates. And we have one where the flaring from the internal reconnection definitely begins well before we see any signature for the breakout reconnection, with the circular ribbon and all of that, which comes later. So in that case, it seems as if the tether cutting really is working independent of the breakout.
Quite possibly. Now, there's two things, right, which I guess Spiro can confirm. But so there's the A, breakout harder to see than the flare reconnection is, right? B, could be tether cutting, could be an ideal instability. See when you do see that kind of crink.
But you you get the flare reconnection making the flare, even if it starts with the ideal instability first.
Yeah, oh, for sure, yeah. So, I mean, you can get, I mean, yeah, we can talk more. I think it's really easy.
One more question?
Kind of a comment. When you went back, go back when you started and Spiro said, hey, it's got to be asymmetric and then you'll get a jet. What we see observationally is that what gives you the filament on one side is there's the included polarity undergoes flux cancellation on that side for days or hours, and then that's where it erupts from, and you get a filament that builds up there.
I think that's ongoing work, I think, with ARMS now, is understanding the flux cancellation stuff too. Doing a jet configuration would be fun.
Okay, thank you, Peter, again. And let's move on to the next speaker, Jiong from Montana State University.
Thank you, Jim. Thanks, Bureau. So the new title for my talk is When Field Lines Break. So the some of the events and were campaign events identified in the EC and IC workshops. I also want to acknowledge this solar flare energy release collaboration, and of which Spiro is the co-leader. And also this gives me an opportunity to actually collaborate with Spiro, writing papers together and with some of the authors in the audience. When we start to write the paper, right, the co-authors put together the BIP files. So at the end, I got a collection of a huge, gigantic BIP file, and with about 2,000 entries. Some of the entries are repeated. And there is this one paper that is repeated so many times, I keep deleting it. Okay, this paper was published in the APGA on January 1st, 1999, and also by Spiro and Jim and Rick. So that's it. Okay, so come to the work, the motivation. So where energy release occurs in the corona, right? So as observer, I don't see the field change. All I see is the plasma reaction, and they become bright or less bright, and over the time. So here is my working assumption. Then I'm going to say plasma emission at the base of the corona will increase, become bright, when overlying field lines become shorter. Okay, otherwise, and the plasma radiation is going to decrease if field lines become longer. And then if I can identify all those places and see the time-spatial sequence of a brightening and dimming, then we get an idea of tracing the coronal structures that are undergoing dynamic changes. So fine print, the dimming in the study refers to the diminished emission observed at the base of the corona. So in that way, and one thing, we can minimize the projection effect from the corona. And second, the lower atmosphere, and we have access to the magnetic field measurements. And the third, observers are supposed to provide ground truth, so I'll look at the ground. Anyway, so how field lines can become longer. So here's the model by Spiro, and 25 years ago. So you see the, what do I click to? I'm getting crazy.
It's the very top button. Just press it for about 2 seconds and you'll see.
Top or bottom? You get the whole talk, right?
Press and hold.
Okay. Okay. Okay, here. Yeah, so here's the model by Spiro. So you are familiar with that already. So we have a quadrupole structure here, just half of the space. When you have the green lines, the blue field lines, and the overlying red field lines reconnect, breakout type of reconnection, right? They generate the green field lines. So blue lines become longer. So then at the bottom, the plasma at the feet of this blue line suddenly see the roof lifted up. Okay, so then they expand, so to speak. Then on the other hand, if we start to switch the direction of those arrows, now the other way, the green field lines, the longer ones, they come together and reconnect and generate the blue lines that are shorter. Okay, field lines in this way is shorter. I call this, then in this case, the plasmas in the blue field lines, they are trapped in. So you can call it a break-in kind of reconnection. Since Romo is in the audience, I'm going to call it the tether cutting reconnection, okay? If you hear Hudson is in the audience, that's implosion. Anyway, so those are the two scenarios. The field lines can become longer or shorter. And then, as I said, observers don't really see what field lines are doing. All we see are just the plasma response, then how plasma is going to respond to those changes. So I'm looking at the pixel light curves at the base of those field lines or magnetic structures, and then try to see and what's the plasma radiation. And here is one type, very typical type of the light curve in the transition region or upper chromosphere. And you see that a sudden increase of a brightening, impulsive brightening, that is a signature of reconnecting, and that release energy and impulsively at a low atmosphere on the time scale of alphonic time scale. So a few seconds to a few minutes. And shortly after that, and you see that emissions decreasing. However, there's prolonged brightening and in the same place for 20 to 30 minutes. And that basically gives you the idea of a plasma trapped in. That time scale shows the evaporation as well as elongated heating and gradual cooling. So that is the basic signature of a break-in type of reconnection generating shorter field lines. And there's a second type of field line, or I'm sorry, the light curves, when you see, again, the sudden impulsive brightening, and again, as I said, that's a signature of a breaking, reconnection, releasing energy, but then it just decreases as fast, and then get to the level even below the pre-flare and pre-eruption and level, and that is a signature of a plasma is moving out along expanding or open field lines. So that kind of a breakout, kind of a signature of the reconnecting, generating those field lines. And every now and then, we get a third type of the pixel light curves, right? And in this third picture, you see the apart from the break-in or out type of radiation, and before the brightening, you get a slow, gradual dimming and lasting for tens of minutes. So that basically shows that there's there above the plasma element, the coronal structure is expanding slowly. Okay, so, and in my experiment, I'm trying to just identify all those places and try to find the time and space sequence of those places and then try to understand what they tell us. So I'm going to show you two examples. The first one, so this is the eruptive event and then with the CME, and you can see that you can see the flare ribbons, right, at the core region. Those are the feet of the closed field lines. But then extending from there, you also see those two ribbons, and then in the bottom right, and you get two dark ribbons. Those places, actually, plasma radiation is decreased. Those are dimming ribbons. The left dimming ribbons and the right dimming ribbons. If I try to look at the pixel light curve at those places along the two dimming ribbons, so this is what I get, right? This is the familiar breakout type of radiation, and you see at the bottom of the coronal structure, so in all those three wavelengths, and the left-hand side and the left dimming ribbon and the right, they all have the same behavior. And then so where are those places and what field lines they actually what field lines are anchored to those places? So if we map them on a magnetogram, again, those blue parts just show a time history of the dimming. And then you can see that right-hand side is a magnetic field, the potential field extrapolation, showing that those dimming ribbons map the feet of an overlying arcade. It can be green arcade or brown or dark brown. And those field lines are opening up, okay, by reconnection and with the underlying structure, and then plasma get out. So this is the one example of a breakout type of reconnection, allow plasma to eject. And then the second example, and now in this example, I'm going to show a variety of dimming brightening sequence. And here in the left panel, and just a sequence of 3 images, and observed by AIA at the wavelength 304. Again, we are looking at the base of the coronal, the transition region, and before the eruption, the top, in the middle, and when the eruption starts, and at the bottom after eruption. Eruption is defined by the coronal mass ejection, okay, and seen by the stereo observation. And then the right panels, we get to see the ratio image, right? So prominently, we get 2 big regions, and in the orange box, and that you can clearly see the dimming signature. So those regions become darker, right, at the onset of eruption. And also, those are the 2 regions at the feet of a filament you can identify. Now, if I try to find the pixels, right, and in those dark regions, and try to see what's the behavior, time behavior of the radiation at those pixels. Then this is just a human version of machine learning, allow me to identify some 10,000 pixels. And among those 10,000 pixels, about 60% and exhibit behavior in the right-hand side, something you're familiar with already, and that's a sudden increase of a brightening and a break, and then the sudden decrease of radiation, right? And the rapid dimming. So those are, again, the signatures of breakout type of reflection. But then the other 40%, those pixels, actually show a different kind of a profile. Before the break, the impulsive rise of the brightening, you see the slow, gradual dimming over time scale for 30 to 50 minutes. That's also the time before eruption or in the early phase of eruption. Okay, so we get to see the dimming or indicating the slow expansion, quasi-static expansion of plasma or coronal structure, and overlying those pixels. Then what is really the time-space sequence of those pixels? So here is, well, I see if I can run the movie. Okay, here we go. So this is just a movie, okay? And the bottom right, and I'm trying to show you where the dimming is taking place on a manogram, and the color just shows the time sequence when the dimming is taking place where. And in the left-hand side, that's a movie, and just showing the where and when the brightening is taking place. So this way you can get a kind of a relative relationship between brightening and the dimming in time and space. And on the top, and that plot shows that if we just sum up all the flux, magnetic flux underlying the brightening pixels, that's typically how we measure the reflection flux. Okay, so of course there's too much information in this, right? Let's break it into pieces. So the first one, okay, so in the early phase, and that is before the onset of eruption, defined again as by the CME observation. So again, the right-hand side, we have those pixels and mapped on the manogram and showing the early dimming and with a light curve exhibiting a expansion or gradual dimming, okay? And then over like at least half an hour. And then again, and that's probably the signature of the coronal structure and the overlying coronal structure gradually expanding. And in left though, interestingly, and we can identify around the same time period, that is 30 to 50 minutes before the onset of eruption, we get this brightening around, okay? So they're just adjacent to where the dimming pixels are, and also they seem to occur at the outer edge of flare ribbons. So this is just a very qualitative hand-waving picture of possible indication for breakout type of reconnection that opens up field lines, but in a gradual manner. So we can map those places of brightening, early brightening, right? And then the trace of field lines, the coronal field lines connecting to those places. So here's the very rudimentary potential field modeling, and showing that you can see in the east and in the west, the field lines try to connect to the other regions. Okay, so remember that this is just a potential field modeling, and we don't really know that's before the eruption, after eruption. If it's after eruption, then those field lines would indicate the green lines as a consequence of reconnection, and of blue lines with overlying red lines, and as a consequence, the blue lines become longer into green lines, opening up the space, so that we start to see the dimming, that is the gradual expansion of a plasma. Okay, so this is the one instant. The next instant, of course, we can also look at the other group of pixels that give you the sudden brightening and followed by sudden rapid dimming. So those are the places we get those tend to be, at those places, this kind of light curve and tend to show up after eruption. So when the CME is already ongoing, and then again, so the nature of those field lines and the anchor to those places probably is up to debate. But if you can measure, right, and what's the flux of those expanding or wrapping structure, and that's of the order and below the 10 to the 20 Maxwell. And on the other hand, the brightening pixels would give you kind of a reconnection flux of order 10 to the 21 Maxwell. Okay, so those are just two examples, and with that, I'm going to wrap up, and hopefully I convince you that the pixel light curves have a story to tell us, right? And then we see the rapid dimming and occurs after eruption and preceded by impulsive brightening, implying reconnection opening up field lines. But we also see every now and then the gradual dimming prior to eruption or in the early phase of eruption, and that may indicate expansion, and in this event, it's preceded by the adjacent brightening at the outer edge of flare ribbons that form later. Okay, overall, those signatures allow us to reconstruct the topology sequence of the interaction between different coronal structures, right? Such as that kind of interaction that is break, that is reconnection, and out, and in terms of the either subsonic expansion or supersonic eruption. That's my talk.
Thank you.
Thank you. Before I take questions, I do have something to say. Many years ago, and when I was a postdoc, and giving some of the firsts, and every now and then, I didn't know how to answer those questions. And there would be that one person who always stand up from the audience to help me out. For 20 years, this picture has been clear in my mind. Thank you, Spiro.
Questions?
I have a comment here. I think this work is so important because really we can't see the reconnection in the corona directly. So the only thing we can do is infer it from its signature on the chromosphere and in the lower atmosphere. So it's so important to be able to kind of see what is reconnecting where. Admittedly, it's not perfect because what you're doing is you're putting in a model as to what you think is going on to give the sequence you see, but it's the only constraint or the best constraint we have on the reconnection that is taking place. So let me ask you, you did all this by hand, or how did you actually do this?
By hand, yeah, I say a human version of machine learning.
It was by hand there, okay. But in principle, you could train a machine to do this. Because it'd be really important to do this for a number of events and see what we learn.
Sure, thank you, yeah. A lot of work to do, sure.
Very nice talk. When you say dimming and brightening, you're probably thinking about, are you thinking about like lower layers rather than the loop extending?
It's lower at the base of the corona, that's right.
Right,
yeah.
right. Does it matter which channels you're looking at depending on the temperature? Are they behaving the same way or differently?
Yeah, currently I'm using the 304, and that's a transition region line or low corona, so you see that, yeah.
Any more questions?
It really shouldn't matter what channel you use as long as you're certain that that channel is in the transition region.
Yes.
The transition region can be very, very hot.
Yeah, but well, there are really a couple of channels I did look at, right? Like the carbon force 1600, it's very difficult to see. So really, it's a little bit tricky. If you look at the transition region, trying to find dimming signature is usually not as easy as the conventional way of finding coronal dimming by looking at the UV lines. Yeah.
So you're saying it's not a measure of the pressure. You have to get very deep, then that's an indication of energetic particles penetrating deep. Otherwise, the transition region emission is kind of a pressure gauge.
That's it. That's the thing I didn't say. Yeah, that's an excellent point. I actually, we have been trying to use at least the gradual dimming to get the expansion speed, but the underlying principle is really the pressure gauge, the transition region radiation, and as a pressure gauge, especially if the overlying corona is quasi-static or steady state expansion. So that's how I get the expansion speed of 10 to 100 kilometers per second before the eruption. Yeah.
Thank you, Jiong. And let's thank all the speakers for the second session this morning. I'll give you the mic for lunch, right?
Yeah, we're at lunch now. I'm so excited about all the talks. Yeah, so the lunch should be outside, buffet style. Go and grab a plate, and then find a seat anywhere. As I say, we have tables out there in the atrium. It may be warm enough outside to go and enjoy the fresh air. It's up to you. And we'll come back. I don't have my schedule with me. What is the time when we come back? 1:30, thank you, sorry.
Oh, excuse me.
I know. Too.
Take your time.
Yeah, thanks, Jim. Tanya? Tanya, yeah. I didn't know she was working with you too. Yeah. She shows up in our. Horace and Irish. Me? Yeah.
All right. So let's go ahead and get started with the next session. First, we're going to have Jiong Sun talking to us about magnetic breakout and coronal condensation.
Sure. Okay. Welcome back. It's a great pleasure to be here with everyone and celebrate Spiro's spectacular career. So the topic of my talk is on the so-called late phase solar and stellar flares. And coincidentally, they have to evoke two of Spiro's action and coronal condensation. So you can find the details of the work in, let me see if I can, in these two papers. One of them is was done one solar cycle ago, depressingly by myself. And then the more recent one is done by my postdoc, Kaiyang. All right. So first I will give a brief introduction of the concept of late phase flares. And for the solar EUV late phase, I will explain how that requires a magnetic breakout topology to give you the large loop and consequentially the long cooling time that is required to explain this phenomena. And then for the stellar case, it is quite unexpected that we see a late phase in white light as well. And I will show through numerical simulation that it requires non-thermal equilibrium and coronal condensation to explain the phenomena. All right. So flares on cool stars, as we all know, they are rapid brightening of the atmosphere through the whole wavelength of EM spectrum, and they are due to the sudden magnetic energy release. Now, as on the sun, it is most obvious in the, let's see. Okay, let's see. It is most obvious in the X-ray. This is a ghost light curve. It has a rapid rise within minutes and a slow decay within tens or hundreds of minutes. Okay. Now, this is not the whole story. Most of the energy is actually released in the visible continuum. But for the sun, because the background is so strong, in the TSI measurements here, you can hardly see it because the magnitude is only about 20 parts of per million. Okay. And the visible continuum is usually thought to originate in the lower layers of the solar atmosphere, transition region, chromosphere, or even photosphere, as contrary to the corona. Okay, so the locations of these two kinds of emissions are very different. Now, what are late phase flares? So this was first discovered after SDO launch by the EVE team. And on the right-hand side, you can see the light curve of this Eve iron 16 lines, which probes the about 3 to 5 million Kelvin plasma. And you can see after the main peak, there is a gradual peak that is about tens of minutes or even hours delayed from the main peak. So this is kind of interesting because the energy content of this late phase can be as comparable to the main phase. So they are actually very important for space weather. Now, luckily for the sun, we have imaging observations. So the first examples, the Eve team already proposed that these late phase are actually coming from these longer loops, overlying arcades, compared to the main phase that is from the smaller loops down here. So naturally, if you think about the conductive cooling time, which scales to the loop length squared, you would expect a longer cooling time. So if these large loops are heated at the same time of these smaller flare loops, it will take exactly tens of minutes to cool. So that naturally explains the secondary peak in these warm EUV lines. So for the example that we looked at, this is actually a very nice example. On the top, I'm showing you the light curve again in the iron 16. You see this large secondary peak. Now, if you compile all the iron lines according to their temperature, and the color indicates whether it's an increase in red or decrease in blue, you see a cascade of this peak, more and more delayed as you move on to cooler and cooler temperature. So this is direct evidence that this is a cooling sequence. And also you can see this dimming, that is a signature of CME. Now, if I can play this movie, you see that this active region eruption is pretty complex. On the top right, you can actually see there was a circular ribbon here, and then the late phase comes from the overlying loops. Now, this reminded me at that time of a work led by Sophie Masson on the circular ribbon and the remote brightening. And after we did the extrapolation, and we found that it is perfectly fit. So on the right-hand side is a cartoon that you have seen many times already today. So you have a small bipole embedded in this larger bipole, and almost always you get a null point right here. And then as the arcades are being sheared, you get breakout reconnection, and then eventually eruption. So this particular magnetic topology and the breakout reconnection really gives you a pathway of coupling the energy from this small shared arcade to these larger loops, such that the larger loops are heated at almost the same time as these smaller loops. And then once you inject the energy to these larger loops, the long cooling time will naturally explain the late phase. And a recent survey suggests that about 50% of the EUV late phase flares on the sun have these quasi-fan spine topology and can be explained by this particular mechanism. All right, now I'm going to switch gears to talk about stellar flares. M dwarfs are stars that are cooler and smaller than our sun. They usually have larger spots, stronger magnetic fields, and naturally, as you would expect, they have more frequent flares. And in fact, they have flares that are so large that can be 100 or thousands, tens of thousands times more energetic. Now, the NASA missions, such as Kepler and TESS, both are broadband visible spectral broadband surveys. They looked at thousands of millions of stars, actually, and they found thousands of super flares. And for TESS, for the M dwarfs, what they found here is an interesting light curve morphology. So you still have a sharp rise and then a gradual decay. However, you see a secondary bump right here. That is really reminiscent of what we saw on solar EUV light curves. Now, the numbers are not small, about 7%. And again, the time delay is similar to the solar case, tens of minutes, and the magnitude can be as high as 1,000th of 1% of the total stellar white light flux. It's pretty large. So what is causing this? Because it is so similar to what we observe on the sun, we hypothesize it could be the coronal loops that are contributing to this secondary curve. Okay, but we don't have any evidence. Now, interestingly, this is probably one of the most studied flares. This is the 2017 September 10th flare, and on the west limb, you see lots of emission signature. And interestingly, you can actually see the emission in HMI pseudo-continuum. Okay, and they actually stay there and last for tens of minutes and even hours. All right. This particular contours are actually RESI contours, I think. So basically, loops can indeed contribute to the white light, even on our sun. Okay. Now, if you do a survey of the HMI observations recently, and people have found about 80 or so events for HMI with off-limb white light emission for flares as weak as goes M2. So it's not uncommon. So Peter Heinzel and colleagues looked into the potential emission mechanism and proposed that it is mostly through the free or free-bound emission rather than the more common Thomson scattering for off-limb emission. But the requirement here is quite stringent. You will need very high density, 10 to the 12 and 10 to the 13, okay, in order to, for this plasma to emit in white light, okay. So they propose, Heinzel and Shibata-san propose that they may contribute to white light stellar flare. But because we don't have resolved observations of the stars, really there's no way to know for sure. Now, we've actually thought about a way, and here comes in the 1D numerical simulations of coronal loops. So if we can recreate the signature in numerical simulations of flares, maybe there is a way to get to such high density so that the loops can emit in white light. So this is the work led by my postdoc, Kai Yang. So what he did is to design a suite of hydrodynamic loop models with the MPI MR VAC code. And he chose a particular energization profile. So at the top of this loop, you put in a very impulsive, energy, on the order of 1 minute. And then at the foot points, you put in a more gradual heating that lasts for tens of minutes. So these setups have been used for solar flare loop models, so it's not new. However, we've cramped up the energy content. So the total energy input is on the order of 10 to the 32 and 33. Now, after that, we synthesize the coronal emissions, assuming that the emissions are optically thin, and we calculate the Thomson scattering free and free bound contributions. And lo and behold, we actually get strong white light emission. So I'm going to explain the main result here in these 4 panels. So the x-axis is time, and the y-axis is the loop stretched out as a straight line, and the top and bottom parts are the artificial chromosphere, which we don't use for synthesis. So this part is the loop. Okay. So we have a number density, temperature, velocity, and as you can see, initially, the number density is relatively low in the corona, temperature is high, and then once you start to put in the impulsive energy, the number density increases, but still only on the order of 10 to the 10 or 10 to the 11, not as high. After tens of minutes, suddenly there is a condensation. As you can see, the temperature drops down to 10 to the 5, 10 to the 4, and energy suddenly jumps to 10 to the 12 and 10 to the 13. So this is exactly the non-thermal equilibrium helping the condensation of the coronal plasma. Okay. Now, if you look at the synthesized light curve here, the red curve is the total synthesized light, and the y-axis is the relative test flux with respect to the disk flux. And the sharp rise in the white light actually coincides with the condensation. Okay, so once we start to get these dense plasma in the corona, we start to get white light. As you can see, there's a delay of tens of minutes, and the magnitude is on the order of 1%. So both features match the observations pretty well. And after a while, you can see there's too much plasma on the loop tops after a while, and numerical errors make it slip off through one leg. So this is basically coronal ring. So we've basically reproduced the observational features of these stellar white light late phase with the right time delays and the right brightness profiles. So we argue that this is a possible mechanism for a stellar white light late phase. So even that we do not have resolved stellar observations, through the difference in timescales, we can argue that the coronal loops can contribute to the stellar white light curves. All right, so here is my conclusion. So late phase flares, they have distinct spatial and temporal scales hinting at their nature. And two of Spiro's favorite topics help explain them. In particular, magnetic breakout reconnection helps explain the solar UV late phase, and the coronal condensation helps explain the stellar white light late phase. And I feel like it's you should always keep an eye on interesting phenomena that is outside your comfort zone, and your knowledge in solar physics may help. Thank you.
Excellent talk and excellent point that we should think about how solar physics can apply to astrophysics and also to the lab as well. But let me ask you, in your 1D simulations, metric heating on both foot points, what would have happened if you had, the heating was twice as strong on one side versus the other? Have you run those cases?
Kaya actually did a couple of test cases. You still get, condensation, but it just slips off right away.
Yeah, Jiong, regarding the flare late phase, I had a different idea for what could be producing it. First, your model, it seems to me that that late phase emission is coming from the breakout reconnection.
Yes.
Not really from what we sometimes call the flare reconnection.
Right.
So the idea I had was that both the main phase and the late phase come from flare type reconnection, from the current sheet that's formed when you stretch open the field. But for the primary phase reconnection, you're eating through reconnecting the field that was part of the original central arcade. And if you eat through all of that flux, then you start reconnecting field from the overlying field. And those resulting field loops that are produced are going to be much longer. And so your explanation about time scales is right on the mark.
I actually agree with you. I misspoke. I think what I meant to say is that the breakout reconnection creates a way to move the system forward from the initial, confined structure to the open structure, such that the energy can be coupled from the small scale loops to the larger scales. But the main energy release, I agree with you, it must be coming from the flare reconnection. Otherwise, you won't have that much, energy to heat everything.
Has anyone who's modeled breakout found that the flare reconnection eats through all of the central arcade flux and you start to reconnect the...
This one this particular event created a CME, so everything actually, at least the immediate overlying loops should have been opened. Yeah.
Any other questions? Okay, thank you, Jiong.
Thank you.
Now we have Erica Palmerio talking about filament eruptions.
Left with the microphone. Where did you leave the microphone? Oh, it's not. Yeah, but apparently online they can't hear, so they want people to be very,
You can use the podium mic. We have a podium mic there. So
yeah, but then I have to talk like this. Very uncomfortable. I test this first. Okay, so, no! What happened? This went, oh wow, okay. I don't know what I did. Okay, since I like Spiro and since Ben built roasting psi modeling, which is fine since I discovered that this is the first child of Spiro. I think it counts, yes. So let's start with the magical world of CMEs. They come in many shapes and flavors. So we have the more energetic active region CMEs, more extreme events that we all know and love. But we have also slower streamer blowout like CMEs, stealth CMEs. I don't want to use the pointer because I'm scared of doing a disaster like before, but for example, the green top right one is the archetypical stealth CME, the Robrecht et al. Event. In MHD modeling, we tend to focus on active region CMEs, mostly because they have easily identifiable sources, they have more concentrated B fields, but sometimes we don't model active region CMEs. So this is a story of how once upon a time, during my perusing of what the sun did in the past, I stumbled upon a giant filament eruption. Now it would be great to have a pointer. What do I do? I'm trying. Oh, I see. Oh, wow. Wow. Okay. So yeah, we have this eruption that starts from the southern eastern limb of the sun. So, yes. So we have here an opening, and then we have this filament sweeping from the east to the west of the sun. And I stumbled upon this eruption shortly after Ben showed me some modeling that he did of erupting the entire streamer belt of M dwarf. That now we know what it is, thanks to Jiong. So I went to him and said, hey, this looks close enough to what you've been doing, but it's on the real sun. And this was, I think, a very pivotal moment in Ben's career, because for once, instead of replying, this is clearly Breakout, he said, oh, we should model it. Yay. Which led to this tragedy in two parts. I meant in two papers. With paper one, we erupted the giant thing. But before we delve into the science, I have a fun story for Spiro. So we started working on, Ben and I started dating shortly after we started working on this event. And this paper was accepted on our wedding day. But what I completely forgotten until I was putting together these slides is that now we all know what Ben was doing the day before he got married. But when I went to Ben saying, man, what happened? It was pointed out to me that there is this paper led by yours truly that was submitted. So now we know what both of us were doing then. So my fake outrage was over, and yes, Ben and I are clearly a match made in the heliosphere. Okay, back to the science. Yeah, it was recognized. Back to the science. So, what was the goal of this paper? For overall goals, can we simulate this complex global variasymmetric eruption with MHD modeling? And can we reproduce the various EUV and white light features that we display in the observations? And can we use the MHD results to interpret the complex observational signatures? Now, this eruption was complex not only on the solar disk, but also in the coronagraph, because we can see this eruption evolving in basically 3 stages. So we will start again. So we have first a kind of streamer blowout-like eruption, then a loop that sweeps the entire sun, and then a 3-part CME at the end. And actually, in a lot of both human-made and automatic detection algorithms, this CME is reported as at least 2 or 3 different CMEs, but it's the same one. It just happens over a day. This entire evolution happens. So we started modeling the eruption, introducing arms, or here are a bunch of equations and numbers that I don't need to explain at this meeting, because most of this room is more qualified than me to talk about arms. So yeah, okay. If you have questions about the grid, please ask Ben or anyone else in this room. We initialized the magnetic field from a PFSS extrapolation from NSO gongs in optic magnetograms. So here on the top, we have the NSO products. Then here we have the ARMS version. And the coronal configuration then modeled by ARMS, from which we then got the entire configuration of the corona after the relaxation of the steady state solar wind for 100 hours. So here we have solar disk and coronagraph data combining AIA, was that K-Core? It's 2015 K-Core already? Okay, one of those. And then LASCO, and then we have the synthetic white light emission. We have a ballerina doing some extreme dancing and field lines. And you know what modelers say, like, oh yeah, we have good qualitative agreement, we can proceed, which basically means, you know what, good enough, okay. So we went and proceeded with this. So how do we erupt this thing? So we obviously have this very extended polarity inversion line that is spanning the entire visible solar disk and also a bit behind the limb. And we basically energized it by putting some shearing flows with the stitch tool/procedures. For questions, please refer to Joel, who is also here. So we will go through. And this is the resulting filament channel activation and then CME eruption. So we are here looking from the side. So here it's like if we're looking from the east limb. Here we're looking from the front. Oh my God. And here we're looking from the bottom, the south pole. And it's looking exactly like it looked in the observation. So we are first erupting from the eastern limb and then sweeping towards the western limb. And Ben promised that this just happened. It did not force the eruption to be this asymmetric. So it just looked remarkably like the observations. Then here we have flare ribbons and synthetic UV emission, and there is a comparison of what it looked like in the observations. Here we have the CME energetics, and we also calculated the flux, so the reconnection flux that then supposedly went into the CME that erupted. And Masha did also the same. She used her method from her 2017 paper to also calculate, well, not really, an adaptation of that method, because obviously this eruption was so large and the energy was dispersed through such a large area that we didn't have very clear flare ribbons. But yes, so we calculated the flux and yeah, the comparison between observations and then the ARM solution is here. So we're looking pretty good in terms of consistency between the two. And then here we have the coronal evolution, where again we have this asymmetric kind of eruption, starting first from the eastern limb and then sweeping through the west. And then we also created J-maps along the eastern limb part and the western limb part of the eruption. And yes, the evolution looks quite like the observations, but by fitting all these points and getting a velocity, the ARM CME is about 1.5 times faster than observed. But what's a factor of 1.5 between friends? Ah, no. Okay. Now we have a bonus pretty movie. Okay. So here we can see the eruption from the corona. Yeah, so we have the eastern limb eruption, then the filament, or well, here we don't have filament material, we have the thin line sweeping, and then we have on the western limb something that actually looks by itself like a three-part CME, exactly like we see in the coronagraph data. But then we thought, what would this thing look like in a synthetic in situ trajectory? So here we're looking from the eastern limb. And yes, Ben cut a few trajectories, but then the one corresponding to Earth would be, okay, here the time is going from right to left, and we're crossing the CME, and we have components of the magnetic field, theta and phi of the magnetic field, speed and density. And we have a configuration that is of the magnetic field that rotates from south to north in the theta direction and points towards the west in its axis. And guess what? This CME was actually encountered in situ. And so here we have magnetic field magnitude, components of the magnetic field, and theta and phi, and speed and density. Here the time goes in the correct direction from left to right, and we do see exactly the same kind of rotation. So we thought, okay, can we actually model this kind of giant eruption in a real-time-like setting? Which led to paper 2. So here our main questions were, can we simulate the interplanetary propagation of this CME as I said, in a real-time-like setting? Can we identify the most important feature to consider when setting up the CME input parameters? And can we reproduce the in situ observations at Earth and the related CME effectiveness? Now, there is no ARMS heliospheric module, so we had to outsource our efforts to the Euphoria folks. So here I will give a small introduction on the model. So Euphoria is computing the time-dependent evolution of the inner heliospheric magnetic field and plasma environment. It uses a combination of empirical and physics-based approaches. Here we are in the US, so I assume that most of the people are mostly familiar with ELIL. Yes, so it's basically the European version of ELIL. There are two spatial domains. We have a coronal domain that is very WSA-like and goes from 1 to 21.5 solar radii, where we are constructing the magnetic field model of the coronal large-scale field. And then we have the heliospheric domain that goes from 21.5 solar radii or 0.1 AU to about 2 AU, depending on where one wants to get to. And here we're using then the coronal domain outputs to then drive the ambient solar wind and interplanetary magnetic field. And when we insert CMEs, they have to be inserted there. So at this inner boundary of the heliospheric domain, which means that you already need a set of input parameters to insert into the domain. You can't just erupt it and see what happens. So we went into deriving the CME input parameters. So for the magnetic structure, we could use solar observation. So we saw left-bearing barbs in this giant filament, which yields a right-handed flux rope. The axial field was directed towards the west. For the magnetic flux, we could use the ribbons arcades evolution analyzed by Masha, as I mentioned before. But then what do we do for the geometric and kinematic parameters from coronagraph observations? And that's because, so these three images of these three parts that I told you about, so the streamer blowout like, the loop, and then the three-part CME, so these images are over 12 hours. So there is no way of making something that incorporates everything that we can numerically put into these models. So we had to do some choices, and we tested three descriptions for the CME ejecta. So for the first, we went with the simple spheroid. So we used all the three coronal reconstructions that I showed in the previous slide to launch the CME in three parts, because in this description, the ejecta is a hydrodynamic pulse. There is no internal magnetic field, so we were just superposing these three pulses to give this extended, very asymmetrically propagating structure. For the second, we used a spheromac, but we only consider the middle part, so the central loop that we saw in coronagraph data, because that was the part that we were interested on. We were interested in modeling something arriving at Earth. In this case, we have a spheromac, so the ejecta is a magnetized sphere. It doesn't have legs. And for the third description, we used euphoria plus fried, where fried is something that looks like that, so a toroidal flux rope with legs. And it uses its own coronal reconstruction tool that includes a lot of deformation parameters, so we were able to give it a lot more asymmetry without basically overfitting like it happened with the classic croissant that is very symmetrical. So yeah, we have this ejecta that is croissant-like, deformed, and with legs. This is the jungle of input parameters. So you can see that for the spheroid, we had 3 CMEs. For the spheromac, we have all the parameters. And for fried, we have all these extra parameters of the deformation. So pancaking, flattening, skew, which says how much one leg is in front of the other, and so on. So here is an overview of the 3 different simulations in interplanetary space and a comparison with ARMS. So as we saw, so here we're looking from above in the left panels and from the side in the right panels. So for the ARMS plus teach me, we have, we saw that in the eruption we had this asymmetry going from east to west. But then in interplanetary space, since we had a fast solar wind stream to the west instead, this asymmetry kind of reversed, and we can see it mostly in the euphoria plus fried simulation. So the leg that the part of the CME that was more in the front was the one in the western, on the western side in interplanetary space. For an overview of the synthetic in situ time series at Earth, here we have magnetic field, X, Y, and Z of the magnetic field, speed, I'm repeating the speed also here, density, temperature, plasma beta, and DST index. So in, fine, thank you. For the euphoria plus spheroid simulation, we are basically, the results are virtually indistinguishable from the ambient run. We only see a little difference here, but basically indistinguishable. From the spheromac, which is the green one that we can see popping up in some cases, for example, here, it's arriving a bit one day too late, and it is resulting as an extremely weak glancing encounter. For Euphoria plus Fried, we have a spot-on arrival time. The impact is pretty weak, but the magnetic structure is in agreement with observation. So if we do, oh yeah, and the CME here was here, this part. Oh. And if we do a zoom in on the CME and on the Euphoria plus Fried results, we're considering not only results at Earth, but here the shaded blue areas are showing plus minus 10 and 5 degrees in latitude and longitude around Earth. So we are missing the compression at the back of the CME that we can see. No, that we can see. That we can see in the data, and that's most likely because we are missing the second half of the fast stream in which the CME was journeying through. And yes, the DST predictions, even if we consider all this cloud of observers around Earth, goes to around minus 50 now Tesla at most, but against the observed minus 68. So we're still underestimating a bit the geoeffectiveness of this structure. But overall, for a very quick summary, we can reproduce this complex eruption and its main observational features with our current MHD modeling capabilities. Yay. And we can try to identify the main characteristics to focus on when modeling the interplanetary propagation of this kind of huge events that at the moment we couldn't figure out a way to erupt the entire thing. So we had to select the portion of CME that we were interested in, which means that here we have to consider some caveats. So for example, if we're in a context in which you're interested in modeling and predicting the impact of such a large event at multiple points in the Eurosphere, then you probably would have to use the unmagnetized sphere, because in that way you can just superpose impulses and see where they get and try to predict the arrival time. So there are, for this kind of events, there are some considerations to be made when we want to predict them in real-time settings. But there is always things that we could do better. So here are ideas for passion projects for Spiro to pursue. That's all for you, Spiro. So number one, we could model the full sun-to-Earth journey within a single model. So Spiro, you will have to write ARMS interplanetary module without bothering Rick. Or number two, we could improve the thermodynamic description of the corona. So Spiro, you have to solve the coronal heating problem before Jim. But what's important, we have to improve the ambient solar wind solutions in MHD modeling. So Spiro single-handedly will solve the whole Eurosphere. Thank you, and long live Spiro. As easy as it seems, I swear.
Oh, I'm sorry. Did you get your pseudo DST by just using a model that takes the simulated solar wind input?
Yeah, so here in the plot, so WDC Kyoto, and the stuff in the line in black is the DST model from wind observations. I think that we use the O'Brien et al. 2000 model, which, yeah, okay, it's 24 years old, but it follows the real DST pretty well. And that's also the same algorithm that we use for modeling with Euphoria, yes. So we compared directly with the modeled DST from wind, which is also very close to the actual measured one. Of course.
I mean, I got to ask this quickly because I got a lot of work to do. But anyway, in that stitch simulation, how was the stitch parameter set? I mean, did the whole prominence erupt or only part of it erupted? So you guys put shear only along
the shear was put along the entire polarity inversion line, and it erupted from the east and followed through the west.
But the polarity inversion line usually is a closed circle, right? I mean, so did you actually have a prominence or a shear that went all the way around?
My darling, did you have problems?
Okay. Put the shear on there. The whole front part, which you saw erupted. Okay.
Sorry, I can't run back and forth. Anybody else? All right, thank you, Erica.
I'm Mark.
Now, Mark Linton will tell you all about how important coronal currents are.
Maybe.
Just give us 1 second, please.
No problem. Well, the slides are coming up, so I want to start with saying that, of course, we're all here to celebrate the career of Spiro. And I figured a good way to think about that is as a story. Work better if Spiro is the creator and Breakout is the hero. And then, of course, any story to be entertaining needs an anti-hero. And in this case, the anti-hero is the torus model, the torus instability. So I'm going to talk about pieces of the torus instability. The torus instability, let's see if I can get the there we go. So here's a picture of a torus unstable coronal mass ejection. You have a current channel here with a lot of twist flux around it, a flux rope. We've heard a lot about flux ropes today. And there's a force between this and the photosphere, or this and the notional closing of this current channel below the photosphere that's been explored in the tokamak community for a long time, and that drives the CME to erupt. We've heard a lot about this today in terms of whether there are flux ropes or not. There's been a long debate. It sounds like listening to talks today that that's largely resolved. Manolis argues that there's a paper with Spiro on it that says that this is all, the difference between a flux rope and the torus instability and sheared arcade and breakout is, there's not a big difference. But that's not entertaining anymore. There needs to be some more to this. And Spiro even said that to me recently. He said a year or two ago, you know, I go to these conferences and I give talks about breakout, and where are the torus instability people? They don't stand up and give me a hard time anymore. Like, it's not fun. So I took that as a motivation to look at the torus instability and to see if I could resurrect one of the arguments. So I've been working with Spiro for 25 years, on and off, and we get into lots of arguments only when we're working together. When we're competing, we don't get into arguments, then we're fine. But the fun part is when we're arguing. But for an early part of the career, I agreed with Spiro about what the sheath currents must be doing in the torus instability. And in fact, there are no sheath currents in the torus instability. So what is a sheath current? A sheath current is what would turn off the twist flux created by this core current so that you wouldn't see the twist flux beyond a certain radius. And Parker summarized that very nicely in 1996. He says if you take an untwisted field that's going through the corona, a nice potential field, and you localize the twist at one of the foot points, as you must, there's no twist going all the way around the sun, no shear field going all the way around the sun, then you're going to generate a local current channel that creates twist and a sheath current around that will turn it off. And that makes a lot of sense. I agreed with that. I was a big proponent of that for decades. And that's a problem with the torus instability. We would always bring that up as a reason why the torus instability has flaws. It requires a core current in the corona does not have a sheath current, what we call the bare current. The breakout, I'm sorry, it's cutting off at the bottom here for me. Yeah, the breakout does not have that problem. It's generated by shear fields. You've heard a lot about that today. That naturally generates core currents and sheath currents. Interestingly enough, Terry Forbes, in a hidden paragraph in his 2010 review of CMEs that Slava Titov, a proponent of the torus instability, pointed out to me, argues against that in what could be a convincing way. He says that in the low beta corona, sheath currents from twisting do not need to stay near the core currents. They can propagate away. And he cites Cecile Delaunay et al. In 2008 to demonstrate this. And so what she did and the team did was they took a localized shearing profile at the base of the corona in a potential field and sheared it up. I don't know about how much, but probably like crazy so that it erupted. But what you can see here is there's three contours of current here. There's a positive one that's yellow, a positive one that's orange, and a negative one that's green. So the positive J dot B is J dot B, so you can tell. So J dot B positive is a sheath current, J dot B negative is the core current, and that's this green slinky down at the bottom. And what happens is, as Terry Forbes points out, this sheath current, while the core current stays localized until it erupts, the sheath current rapidly propagates away from it. And so as far as the core current, I think Terry would argue, once the sheath current is pretty far away, it sees essentially that it's a bare current and it can erupt as a torus instability. So that was interesting to me. Now, I don't do really simulations where you shear the photosphere, but I work on flux emergence a lot. And in flux emergence, see if this will play. In flux emergence, you should have a similar thing. Really what a sheath current does is when a sheath current passes by you, You're in a regime where maybe there's no magnetic field or nothing very interesting. Sheath current passes by you. That tells you something interesting is coming. There's a magnetic field coming right after me that is generated by a core current somewhere far away that I can't see yet, but the sheath current tells me there's a magnetic field coming. So that's what's happening here in this movie. There's essentially, there's no magnetic field in this particular viewpoint, or no strong magnetic field at the beginning right there. And the first thing that comes up is some magnetic flux, and if you looked at the currents, if you could measure those currents, horizontal currents, which are tough to measure, you would see a sheath current coming up first. Or at least that's what we thought. But then we looked at the time in some of James's simulations for the sheath current at the photosphere and could not find it. It was work we did with Tibor Turek, who's another proponent of the torus instability, and he wanted to see if we could find evidence in both simulations and in the corona, or in the photosphere, of cases where you just had a bare current. And he's found a lot of those cases, which was puzzling to me, because I've just made this argument that they should always be there. So what is going on? Shudong Sung, who's here, and Mark Chung made an argument that you could actually fool yourself by just looking at the photospheric field perpendicular to it. And that, if you find, that's all we can measure is the current in the perpendicular to the photosphere. And there are projection effects. Nothing is exactly, no twisting or no current channels is exactly perpendicular to the photosphere. So you're going to mix up different components of the current, and they argued that you're just fooling yourself, that there is actually balanced current. You just don't see it when you look at this one component, and that's obviously true. So then I went back to James, and we said, let's look for this in more detail, and let's not just look at a plane, let's look at the whole corona and see if we can find these things. And here we're looking at, to find something that was drawn in this cartoon in a paper by Pete Schuck. Whoops, find my mouse again. Here we go. So we started in the convection zone, and James, I don't think James is going to talk about this next, but James has done a lot of work on this, and Kalman as well. You start in the convection zone, the pressure the gas pressure is very high relative to the magnetic field, so it confines, or we assume that it confines the flux rope. So there's a core current going in one direction, a sheath current in blue going in the other direction, and you can't see the flux rope when you're out here because the core current has turned it off. Then it emerges into a very low pressure atmosphere, and immediately the flux rope expands, and the sheath current arguably blows off to far distances, and you have a core current with lots of twist around it, and then eventually at some large distance, the sheath current turns off. So that's what we were looking for from this cartoon in James's simulations. And the way we do these simulations is in the paradigm that Yuhong Fan talked a bit about today, where or has talked about in the past at least. You have this flux rope, it comes up, you can see it expands just as I showed. Here I'm showing field lines. There's no current shown here, but you can imagine what the sheath currents are doing. And then we looked at this. So here's again, these green field lines are the confined field lines in the convection zone, expanding like crazy in the corona. You can see the footprint of magnetic fields at the photosphere here. And this cut right here is a vertical cut of current where blue is current going in one direction, and red, there's a little bit of red right here, is current going in the other direction. And this is the sheath current that confines all of this twist flux, propagating out into the corona. And the core current is still right down here at the center. So that looks promising. So we looked at that in more detail. Actually, I took a couple snapshots, or James took snapshots for me. So here you have nothing. So you expect a sheath current to come up, because it's got to tell you there's something coming up. Here's a sheath current coming up for the twist field. We actually did two planes. This is a sheath current. You also need a sheath current for the axial flux of the flux rope. So the flux rope is going left to right here. So there's sheath current for the axial flux in this plane, sheath current for the twist flux in this plane. And then they both rise up as the magnetic field expands into the corona. The sheaths have to propagate that ahead of them. And then eventually you see the core current of your twist flux right here, and then eventually the opposite directed sheath current of the axial flux when the axial flux starts to split off. So it really does look like you're obviously, it was a relief to me, you do have these sheath currents, as we always thought, both with twisting, as Delaunay et al. Showed, and with flux emergence, as James has shown in these simulations. You have a sheath current that comes up. So there's always a sheath current with your core flux rope. The question is, how far away does it go? And what is it doing? And it really seems like it can propagate away pretty well. So we then went on and compared it. What are three different conditions? That was a condition where there's no magnetic field in the corona prior to the emergence. So we've done, this is based on a set of models that James did with me and Spiro, actually, looking at emergence into a case with no coronal field, emerges with antiparallel coronal field, so the twist field of the emerging flux is opposite to the pre-existing coronal field, and where the twist field of the emerging flux is in the same direction as the overlying field. I'll just pan through these. So you can see them rising up. In all three cases, you get a sheath current and some core current behind. Here it's just, it's a sheath current that's just between the magnetic field and plasma. Here's a sheath current in a smaller region behind the magnetic field and plasma going in the other direction, and magnetic field going in the opposite direction. And it's been held down a little bit by the overlying field. Same thing here. It gets held down a little bit by the overlying field, but it's harder to see the sheath current when I scale everything the same way. The sheath current here is not separating fields of opposite directions. It's showing a gradient in the intensity of the twist field. And this propagates away more like a wave than like a sheath. It slowly rearranges the corona to be no current sheets, but in a slightly different configuration than it was before. And you go on like this. This figure right here is dear to Spiro's hearts. This is the breakout reconnection ensuing in a natural way, like he suggested we should do this morning. You just have this rises up, you get a breakout reconnection up here, the side lobes are forming on the sides, and the other two are just continuing as they would. And then this, I won't show it, but this eventually gives you a breakout. This, interestingly enough, is the topological configuration for the torus instability, but we didn't put in, I guess, quite the right parameters. It doesn't erupt. That's still a question whether we can get this to erupt or not, but there is a core current. The sheath current here is pretty far away, so it's got that one ingredient, at least, of the torus instability, and James and I would like to look at this in more detail. But that's the main story. There is a sheath current, of course, but it propagates pretty far away and kind of integrates itself into the background corona. So you have a core current, this red piece here, that's sitting and can form actually the core of a torus instability. So that's the story here. The electric currents behave as they're expected. We've been fooled, I think, somewhat, as Sun and Chung argue, by the projection effects on the photosphere. And also, in particular, I was fooled by the sheath current rapidly propagating away. I think we looked too late. When the first time we looked too late in James's simulation. It already propagated away. But the fact is they're all surrounded by sheath currents, but sometimes they're really far away. For the torus instability, that's good news. The sheath current can easily propagate away and leave behind a bare current. And for the breakout, well, it naturally creates a sheath current, so you can do that with shearing or with flux emergence. And so, good news, Spiro. There's reason to stick around. There's still an anti-hero. The torus instability may still be alive. Thank you.
A key point, though, Mark, is on the right, though. Do those field lines have twists or not? The ones that have emerged. Those things are all kind of sheared arcade.
Well, James has looked at these. These are sheared arcades when they first emerge, and then they all split off. There's this reconnection that happens right about here in all three of them that then starts to form. Like in the breakout, that's called the flare reconnection. There's a bit of that in each of the other ones as well. So they do start to form a flux rope. But then these two on the side don't erupt.
One in the middle erupts. Okay, so that probably hasn't been enough reconnection to give you...
Not enough, yeah.
Well, Mark, interesting talk. Just to make sure, down there in the photosphere, you do have sheath currents because you have flux tubes that embedded in relatively filled plasma. But how far high in the corona do you think sheath currents go before they give way to the volume, filling magnetic field and the core current, the volume current?
Yeah, so first of all, this is one without the currents cut off at the photosphere. So you can see it's a big mess in the convection zone. There's lots of forces, lots of currents in different directions. Yeah, I think philosophically these can go, I mean, if you started the sun from zero with no magnetic field and you started emerging it in a clean state, that sheath current goes all the way past the Earth. Otherwise, you would never see magnetic fields at the Earth. So at some point in the past, there was a sheath current from magnetic flux that emerged from the convection zone that went past the Earth. And then anytime you're emerging new flux and you change, like particularly a new solar cycle, you change the direction of it, that gets propagated out by a sheath current.
Sure, but that's a different thing. I mean, you
have it's the same
beta.
Thing. That's the same thing.
Well, you have beta going through different regimes if you move into the inner heliosphere. I'm talking about the corona mostly. A few tens of megameters above the photosphere. What happens there? Do you still have sheath currents?
You have sheath currents going out until it comes into until the force balance between the plasma pressure and magnetic field outside of the sheath current and the magnetic field inside the sheath current balances, and then it'll stop moving. But it's gonna even then it has to perturb the outside a little bit. If sheath current moves out, it's going to occupy a volume. The whole corona, in some sense, is going to know that the whole corona had to occupy a slightly smaller volume, increase the whole magnetic field by just a little bit, maybe not detectable, but philosophically it's there.
I'd just like to point out that the sheath current doesn't have to be a thin sheath. It depends upon the twist profile of the flux tube.
Sure, yeah. Yeah, and particularly in the case where it's emerging into the same sign, it immediately starts to spread out and becomes, at least at the color scale we used, you can't even see it anymore, but it's still there. But yeah, it spreads out. In the breakout, it stays nice and thin because it's forming a current sheet.
So what parameters do you think you need to change in that simulation to get it to erupt? Do you have a sense?
James and I have debated that, and we talked with the torus instability group about that, and we're not really sure. I mean, certainly the decay index is a critical part of the torus instability, and ours, I don't think ours was particularly good for that.
The sources of the overlying field closer together, right? That's how we get to faster decay to give the eruption. How we would change our initial conditions to result in something like that is really difficult. So,
First state, where you have no field to begin with, that has infinite decay index, and yet it still doesn't erupt. So the emergent field creates its own decay index.
Yeah.
So that's the whole point of what I was saying, is that we need to do calculations in which we have a kind of like a self-consistent as much as possible. Admittedly, you have to assume some initial state for the emergence, but we need to have simulations like that where we don't precondition the system to give us the eruption that we'd like to get. And in this situation, you've done that, and you found that in one case, yeah, it happens naturally. In the other case, no, it's not happening. Now, let's just see what you could do to make it happen. But I bet you it's not going to be so easy.
Yeah, so that's a very good point. In that case, the only thing we have to play with is what is the profile of the flux up in the convection zone. And certainly, we picked one. There's an infinite number of solutions. That's something to try.
All right, thank you very much, Mark. Next, we have James Leake, who will talk to us about the photospheric imprints of coronal currents.
So top is forward. Okay, so this is work done with Pete Schuck, theory group that has, been influenced and directed by Spiro for many years. So thank you, Spiro, for your help. What I'm going to talk about is the photospheric imprints of electric currents in the corona. So we've heard all about how magnetic reconnection is integral to the onset of eruptions, and this happens in regions of strong gradients in the magnetic field. The problem is the best observations lie in the photosphere. So we resort to simulations, extrapolations, to determine the field in the corona and then look at those currents to analyze the reconnection. This is an example of a simulation that Mark showed. This is a simulation we ran with Spiro, 2022, showing the emergence into an overlying field. And I've kind of highlighted the here we go. I've highlighted the this is freaky. Highlighted the sheath current, the core current, and what we call the flare current sheet, which in these simulations is what precedes the fast rise of this flux rope into the corona. So I'm going to present something a little different today, which is the use of two mathematical methods to look at the photospheric imprint of these types of current systems, because that would be great if we could actually detect such a current system in the observations. So I'm going to write myself out of the comedy award by presenting a talk mainly of equations, but art is subjective anyway, so let's just go for it. So we're going to start with the fundamental theorem of vector calculus. Any vector field can be resolved into irrotational and solenoidal fields. So B is curl of A minus grad phi. So let's consider a volume in R cubed. So volume V, we have the Helmholtz decomposition in that volume gives us the vector potential A and the scalar potential. Both of these potentials have a volumetric term, volumetric sources, and boundary sources. So S is our boundary of our volume V, which is sitting inside R cubed. Why does this not advance? Forward. Here we go. Okay, so what does this look like for a magnetic field? We write curl B as J, ignoring the displacement current, divergence of B is 0. So we lose one of the volumetric terms. So what we have is an integral over our bounded volume V of the electric currents inside the volume and these boundary integrals. You'll notice the first term looks like the Biot-Savart law just applied to our bounded volume. So let's go to the Biot-Savart law. Despite what you learned in MHD, first thing we learned in high school physics or graduate or college physics was electric currents generate magnetic fields. The Biot-Savart law expresses that. So we integrate over all the currents in R cubed, we get the magnetic field. We convolute the currents with the Green's function, we get the magnetic field. We can divide that integral over R cubed into our bounded volume of interest. And in later slides, this bounded volume is going to be our corona. So we divide that integral into current sources inside the box and current sources outside the box. But we can equate this with the Helmholtz decomposition. Both are valid inside our box V. Okay, so if they're both valid in V, then we can equate the terms. So the first term is the magnetic field created by all the currents inside our volume V. The second term is the magnetic field generated by all the currents outside the box, in the external universe. But it's equal to these boundary integrals in the Helmholtz decomposition. So, if you know B in your little volume, say you've got a little simulation of the corona, if you know B, you can estimate what is the field due to all the currents inside my box and outside the box. And you're all asking, so what? So let's say the box is our corona. And we know B because we have an extrapolation or a simulation. We might want to know what is the field that is generated by currents inside and what is the field that's generated by currents outside that box. Or let's say we have a photospheric plane. What is the field due to all the currents lying above that photospheric plane? What is the field due to currents lying below that photospheric plane? So let's take our expression for B again. We have sources internal to V in the yellow, external to V in the green. We just showed that the external sources are just the boundary integrals from the Helmholtz integral. So I don't need to know J in my external universe. I just need to know B on my boundary of my box. If I do, then I can get the field due to all the currents lying in the external universe, outside my box. And if I subtract that from B, I get the field due to currents inside. So just using the boundary integrals, we don't have to do any intensive volume integrals. We can get the fields due to currents inside and outside my box. Now, if you want to see how this plays out for considering helicity and decomposing the helicity into self and mutual, Pete Shook has a poster on this, and you can also see more details in Shook and Linton 2023. Okay, but what I'm interested in today is, let's say we have a current system in the corona. What is the field due to that current system at an observable location like the photosphere? So we can extend the Helmholtz decomposition into all of R cubed. So this is just the same equations I was showing before, the field due to currents inside the box and outside the box. Now we've got to evaluate it outside the box. We have to extend the Helmholtz decomposition. We basically multiply by a prefactor. So it's 1 inside the box, 0 outside. And then it's a different value depending on the boundary, whether you're on a plane or a vertex, depending on the shape of your box. So let's say we have a volume in the corona which includes a current sheet of interest, like the flare current sheet. What is the field of the photosphere due to this current sheet? So we're evaluating the field due to currents in this box down here. So alpha 0 in this case. So we can just equate those two terms on the right-hand side. So now all I need to know is the magnetic field in my little box in the corona that surrounds my flare current sheet, and I can figure out what the field generated by those currents inside that box are. So we can do simple surface integrals. Much quicker. Okay, so to recap, we can use the Helmholtz decomposition to calculate the photospheric field due to, say, a box surrounding a flare current sheet in some volume in the corona. The goal is to develop an observational signature, which could be like a pre-eruptive, current sheet building up before the eruption. But as I pointed out, we don't have B in the corona. We only have J. Sorry, we don't have B or J. We only have B at the photosphere. Luckily, there's another mathematical method we can use to infer the field at the photosphere due to all the currents lying above it. And that is the Chi-Chi method, which Pete Schuck et al. Released in 2022, based on the work of Gauss and Backus. Basically, you use the Helmholtz-Hodge decomposition to break the field on the photospheric surface plane into poloidal and toroidal components. And the poloidal can be further decomposed into field due to currents lying below the photosphere, field due to currents lying above the photosphere, and the remaining toroidal component is fields due to currents threading the photosphere. It's unique. It's also we also have a Cartesian version as well as spherical, and it's open source, available through NASA's GitLab. So, we've got two tools to recap. Chi-Chi can be applied to observations to determine the field due to all the currents lying in the corona above. The Helmholtz decomposition can be used when you know the field in the corona and you're interested in looking at a particular subset of that corona and see what the effect of a current sheet inside that little volume is. If we can use these together, using simulation and observations, we might be able to find some observational signature to look for. So we wrote a code to do the integrations on a simulation domain. It's called Heist. It's basically an open source integration scheme using Python, Fortran, C. Hopefully will be released soon. But basically, if you give it a box with the currents inside that box and the magnetic fields on the boundary, if you want that, it can calculate the field anywhere in R cubed based on those sources. And it will do the fastest approach. You can do either the volume integral or the surface integral if you need to. So a quick slide just to show that we've validated this against known solutions. So imagine you have a wire threading your box. You can calculate, we know the total field and the currents in that system. We can basically calculate all the terms in the Helmholtz decomposition. So we have the total B is the black line, which is overlaid by the reconstruction, which is the magenta. And we have the different components, the field due to currents inside the volume. Blue is the field due to currents outside the volume through the boundary integrals. And when you sum them up and take the difference from the original field, you get the thing on the right, which is the residuals. And we can make those as small as we like, given the time constraints. So the code has caught up with the 200-year-old mathematics. Now we need to just show that the two methods work well together. So as I said, Chi-Chi decomposes the field on the photosphere due to currents above and below. Heist can do the same thing by just doing the brute force calculation if you know the currents everywhere. So we did that for a test case where we do know everything everywhere. And that was, we pulled this from Lucas Tarr and Dylan Key's papers, where they have a toy active region produced by a spheromac emerging through, expanding through a photospheric plane. So we just checked that Chi-Chi and Heist agree what is the field due to the currents above and below at a certain snapshot in this expansion. So on the right here, I've got the field due to currents above in red, below in blue, and green is a total. And Chi-Chi is a dashed line, Heist is a solid. They agree really well. The boundary conditions are slightly different in the two approaches, which gives us difference. But we know the two tools play well together. So now we're at the point where we can start looking in simulations using these two tools. So Matthias Rempel kindly provided me with some data from a simulation by Chen et al., which is basically a magnetoconvection simulation with a chromosphere and a corona on top, and there's magnetic field fed in from below, and it's allowed, the convection is allowed to churn that field up, active regions are formed, and this is some forward modeling in some AIA lines. This is going to skip through. So at about 1.7 in the time unit here, you're going to see an eruption. Okay, it's coming up. There we go. There's the eruption. Okay, so I wanted to look at what would Chi-Chi, if this was an observation on the sun, if we had the photospheric field, what would Chi-Chi see? What would it tell us about the field due to all the currents lying above the photosphere? So I did that as a function of time for the snapshots I have, and I integrated that. So what we have on the top left is the total field due to currents, so basically it's a flux. The flux due to all the currents above in red, below in blue, and total is green. And I'm going to cycle through this simulation, and on the right you're seeing an isosurface of the current density. Go through, on the right here, about 1.7, on the right here, this is the structure associated with the eruption. And this is the magnitude of J on a log scale, the isosurface. The problem is, Chi-Chi can't distinguish that because of all the other currents lying below. The chromospheric currents are dominating the signal that Chi-Chi is picking up. Not surprising. I mean, the chromosphere is very complicated. So what I did was, let's just assume that we can get vector magnetograms a little higher up. So I moved the photospheric the plane of calculation higher. And now when I cycle through, when I get to the point just before the eruption, oops, go back. We look at the field due to currents above. There's a little bump here. If I subtract the mean, we get some kind of signature. There's a slow increase as this flux rope builds up, and there's a drop as it erupts. What I haven't done is done the equivalent integral around that structure to see if that dominates the signal from the Helmholtz decomposition. But this shows that we could use these simulations with the caveat that we kind of have to get above the chromospheric guff to get a clean signal. But this is very preliminary. And I'll finish with some analysis of some more idealized simulations. These are simulations we ran with Spiro. Mark showed these before. We just have an emergence into an overlying dipole field. So we can look at the flare. What I'm interested in is the flare current sheet. So there's the sheath current that Mark talked about. And then this is J over B, so this is highly exaggerating the current structure here. This is the flare current sheet. So let's see if we can see some kind of signature related to that. So again, I can plot isosurfaces of the current density. So this is kind of, if you look from above, this would be a sigmoidal structure underneath the flux rope that is erupting. But there's a lot of chromospheric current density as well, which again kind of masks the signal. So what I can do, like I said, we can take a box in the corona around where I think the flare current sheet is going to form and integrate the field, calculate the field due to all the currents inside here. And then in Chi-Chi, I can say, what is the field due to all the currents above? And that's what's shown on the right. So the Chi-Chi is the solid line, is the dashed line, and the solid line is the field due to the currents just in that box. And it constitutes most of the Chi-Chi signal. So that's telling us that this box is where most of the currents that are influencing the field due to currents above are. The caveat is, again, I had to move my photosphere up to get a clean signal. This time only 1 megameter, but these are more idealized simulations, so they're a little more forgiving. So we can go cycle through in time. So what I'm plotting on the right here, again, is the field due to currents above in red, field due to currents below in blue, and the total in green. So as we go through in time, so the bottom left plot here is like an integral of J through the volume. So it gives you a kind of visual of where all the currents are. So early on, this is the sheath current that Mark talked about. It's just emerging. And that gives us a signal in the field due to currents above in this red line here. As we go forward in time, that signal decreases. Thank you. And then we see a rise in the field due to currents above as the core current that Mark talked about slowly emerges. It forms a sheared arcade. When this transitions to a flux rope, we get the eruption somewhere around there. Now, you're not seeing a clear current, flare current in this because this integral is kind of capturing the sigmoidal structure. So that's why you're kind of seeing 3 bands here. So this is kind of encouraging. We are seeing a signal, but the caveat is we do have to get above all the chromospheric currents. Now, in these simulations, we're really kicking this core current up into the atmosphere. So with a more relaxed approach, maybe we might get a cleaner signal. So to conclude, the Helmholtz decomposition gives you the well-known Biot-Savart law when applied to a magnetic field. And using the Helmholtz decomposition makes calculation of field due to currents inside and outside a volume of interest very easy. Problem is it requires knowledge of B in the corona, which we don't have. But Chi-Chi gives us the field due to all the currents above and can be applied to observations. So the goal is to use these two in parallel and use a suite of simulations to try and develop observational signatures related to the influential current sheets that we are seeing that are related to the eruptions. And I'll finish with, Jim will appreciate a good reference to Shakespeare. The only difference between the tragedy plays and the comedy plays is when the mistaken identity results in everyone dies or we'll have a sing-song. So in this case, we've removed the mistaken identity. But I think we've landed somewhere between comedy and tragedy. So, thanks.
Hi, Jim. Thank you. Very nice talk. Can you go back one slide? You're looking here for a signature leading to the eruptive flare, but you're not sure. I mean, your system, isn't it already unstable to start with? Or, I mean, you know, when we were looking at the helicity, the point that we saw with looking at the helicity in your systems, that it seems that from the start, your system is either stable or unstable. So you may, if you're looking for a signature that will come up telling you the system becomes eruptive, you may not find it because it was already there from the start, no?
Yeah, I agree. I'll go to my conclusion, to my answer is, I think different types of simulations, applying this to a big suite of different paradigms would be really useful. But I'm interested in what you mean by unstable from the start. Is this in reference to the helicity calculations?
It's your system. I mean, you don't know. It seems that you're looking for a signature to detect a change leading up to the eruptive flare.
Yes.
So what? So you're making the assumption there that there is something which is changing, that something is happening that makes the system unstable. While in your simulation, they may be already unstable to start with. At t equals 0, the system is unstable. There is the point of no return is already passed from your flux emergent simulation. As soon as you inputted the flux tube, you know that eventually an eruption will take place.
Well, yeah, I mean, yes, because that's our paradigm. We set it up, we let it go. It goes there. Like, it's completely deterministic. So I guess I'm not sure of the point.
Perhaps to pick up on what Etienne said or clarify, the question is, suppose you to do exactly the same analysis on the other cases which did not erupt, what does it look like? And what would your result there on the right look like? Or what would your analysis give you?
Right.
And would there be kind of some observable signature in the this current decomposition or this current inference procedure that we could use for, say, whether this is a system that will erupt or this is a system that will not erupt?
Right, so if we run a simulation where we know it ends up stable, you're saying, how different would this calculation be?
Look at the ones where they feel.
Well, you'll probably not see this drop. I think that's associated with the flux rope lifting up. But we need more work.
Any other questions? Okay, well, I think we have a break now, and we'll be back here at 3:50.
get off big.
4 p.m., Jim.
I hit a wall like an hour ago.
I've been here for 3 days. This is my 4th day already, so.
Yeah, I've been here longer than you, right?
Oh, right, but it was totally not because of the skiing that we came here.
No,
You didn't do a
That's a
good
true
job.
story.
You didn't do a good job
But that-
defending yourself.
but it was true though. I know. No one believed it.
There's a little timer.
At the posters, what's going on?
Me. It's me.
Oh yeah, that's right. People figure out it's only CalMed. Yeah, we can spend our time more wisely. Yeah.
Yeah, that could be taken a different. Goat is greatest of all time.
All right. Well, here we are, the final session of what's been a really great day. We have the banquet tonight, as I said, right next door. The bar will open at 5:45, and then food will be available, again, as buffet style, at 6:15. Is that right, Cheryl? So, yeah, it's going to be a great evening. Be sure and, was that? Oh, woohoo! Woohoo, indeed, yeah, yeah. All right. So, as I mentioned this morning, this meeting could not have happened without Cheryl Shapiro, who has been fantastically helpful. And not only for this meeting, but also the ARMS users meeting, which was 3 days before this one. You know, Judy.
We had a 3-day, very intense meeting. Cheryl was really helpful for months ahead of it, trying to help us figure out logistics and figure we're going to get in the building and so on. And she went above and beyond the call of duty to come in on Sunday and give Joel and Aleda, badges to get in. So we can't thank you enough. Well, we can, but
Yeah.
she should come up here.
Yeah, so please come up, Cheryl. Big round of applause now. I won't help you up because I know you're a super fit woman. Oh. Yeah. So I was talking to Holly. I said, Holly, I want to, get something for Cheryl.
She said, Cheryl doesn't do gifts, right?
Well, she said, Cheryl, in a very positive way, she said, you're a simple person. You don't like lots of extravagant things, and I'm not sure what to recommend. So I came back, and Judy pulled me aside yesterday and said, Jim, guess what? I got a gift certificate for the dining hall at Chautauqua for Cheryl. So yeah, so this is, yeah. So, and it's
You recommended it to us, and it was fabulous.
and it's beautifully wrapped here. So here you go. On behalf of the Spiro Fest attendees and the ARMS users, meeting attendees, thank you so much for everything.
You're welcome. Thank you all. Thanks, everybody. And thanks for joining us here in Boulder. You've got great weather. I ordered it special for you. I took care of that, like everything else. So enjoy your stay, and please let me know if there's anything at all I can do for anyone. And thanks.
Thank you. All right. I guess the speaker can use this up front. Yeah.
Okay. Hopefully this thing will work. Okay. So our next talk is by Kalman Knieznik from NRL, formerly of Goddard when you were a grad student.
Yes.
And it's titled The Role of Twist in the Emergence of Magnetic Flux.
Student with Spiro about a decade ago, and learning from you and your cat and Rick. And I don't really know how we got through a day without a mention of your cat, but your cat probably knows everything I'm about to say, but I'm going to say it anyway. So I'll be talking about photospheric signatures of emerging flux ropes. And in many ways, this builds on some of the work that we did about injecting helicity into the solar corona. So the basic question that we've been interested in studying is, how do the subsurface properties of the rising magnetic flux ropes influence the observed properties of the emerged active region. And how, in particular, how is magnetic helicity injected? So, we spent a lot of time working on injecting magnetic helicity into the corona by photospheric motions. But of course, you can also inject magnetic helicity into the corona by emerging it from the convection zone and up. And the basic problem that we're dealing with is, active regions are a three-dimensional structure, but all we have is a 2D plane that we can really see. So we want to figure out how to get the or at least infer something about the three-dimensional structure from just looking at the photosphere. Go. Why the slide's not moving? Not going back either. Oh, there it is. Okay, so again, we wanted to try to figure out, just by looking at the photosphere, whether the emerged active region corresponds to a highly twisted magnetic flux rope. After all, these highly twisted flux ropes have a lot of free energy and they're more susceptible to explosive behavior. So what signatures at the photosphere help us determine whether the flux rope is highly twisted? So our approach to doing this was to run numerical simulations using the layer 3D code of flux ropes that rise through the convection zone, the photosphere, and into the corona. And we wanted to vary the twist of these flux ropes, do a parameter study where we vary the twist to see, how the photospheric signatures change. The problem with doing this, and the challenge with doing this, is that if you just imagine a pressure-balanced flux rope in the convection zone, if you make it isothermally buoyant, it's going to rise differently depending on its twist. The rise speed is going to depend on the initial twist of the flux rope. So anything that you see at the photosphere, the effects of twist and rise speed are going to be convolved, and you're not going to be able to figure out whether what you're seeing is due to twist or whether it's the rise speed affecting the properties. And so we wanted to devise a model where we have a simulation that decouples the effect of rise speed and twist. So we wanted to work with a semi-torus as our initial flux rope and essentially balance the Lorentz and buoyancy forces to get it in pressure balance, and then subtract off a twist-independent density to make it buoyant in such a way that it rises at the same rate regardless of its twist. So, just visually, this is what we were trying to go for. You have a semi-torus in the convection zone. We line tie the legs at the bottom, and we make it buoyant, again, in a way that is independent of the twist, and we let it rise. And then we look at what happens at the photosphere. So in our setup, we used the form of the torus from Yuhong Fan's previous work, where you have this semi-torus in spherical that can be described in spherical coordinates. And we devise a model where we basically balance the Lorentz force and the buoyancy force. So it turns out that if you add to the torus this mass density, you can actually make it neutrally buoyant. And this depends on, kappa here is the curvature because you have a tension force. Where is this? You have a tension force pointed down, or inward, and you have gravity. Where is this? Okay, you have gravity, and you have the twist because you have a hoop force pointed outward. So this form of the density, and we derive this in our paper, balances the Lorentz force and the buoyancy forces to get your flux rope, your semi-torus in the convection zone in pressure balance. And then what you can do is you can just subtract off from that initial state a twist-independent density and allow this thing to rise buoyantly. And so what you can see is if you were to do this and just do an isothermally buoyant flux rope, the depth of the flux rope as a function of time would be different, and the velocity would be different as a function of time as it's rising through the convection zone. But with our model, the solid lines here, you can see that for most of its rise through the convection zone, depending on the rise speed doesn't depend on the twist. It's rising at the same rate regardless of its twist. So with our model, we can actually go ahead and look at the photosphere and figure out what properties are determined by the twist rather than having it convolved with the rise speed. So if we just look at a untwisted semi-torus, okay, there's no component wrapping around the minor axis. And you look at the photospheric magnetogram. What you see are two primary polarities first sort of, I did that, emerging over here. But then you see sort of these lanes forming in the middle, these striations, alternating positive and negative polarities. And they grow in time, and you get more and more of them forming, and you get these, a lot of positive and negative polarities alternating. And then if you look at the field lines, you see a whole bunch of, I don't know where this is pointing, serpentine field lines going in and out of the photosphere, up and down. Above them, you have these quasi-potential loops, but near the photosphere, you have these serpentine field lines going in and out of the plane of the photosphere. And as the flux emergence proceeds, the central portion near the middle of the emerging active region basically stays fixed. The other side of these field lines essentially moves out towards the primary polarities to make these quasi-potential field lines. Now this is really indicative of the undulate instability, which has been studied for decades, going back to Parker, Chandrasekhar, and basically what this instability is these field lines, this flux basically reaches the photosphere, and then it has all of this heavy plasma that it needs to lift in order to rise, and it can't do it. So it just kind of piles up. And it piles up until the magnetic pressure gradient builds up, and it's able to emerge through the photosphere. And when that happens, when the magnetic pressure gradient builds up, it basically, part of that flux starts to peak out of the photosphere with an inverse U-loop. The plasma on top of that loop is able to drain, and the flux is able to emerge even more. So the criterion for this instability has been studied also by many authors. It's this ratio, which is basically the ratio of the magnetic pressure gradient to essentially the gravity. And you can plot these two quantities to figure out when, as a function of time, this instability criterion is exceeded. And you can see that these green curves around t equals 780 finally show that the instability criterion is exceeded, and that's basically exactly where when we start to see these lanes forming. So that's really nice evidence that what's happening for these untwisted flux ropes is the undular instability. We can go further, and if we can do a cut, so we do a cut basically sort of in this direction and in this direction of the magnetic field, and we get these curves, these oscillations, right? This is the alternating positive and negative polarities. So we can fit a sinusoid to the profile as a function of time and get the fastest growing wavelength of this instability. There was a nice paper in the late 70s that predicted the fastest growing wavelength of the instability, and it depends on the local pressure scale height. For solar values, it comes out to be about 3.5 megameters, which is exactly what we are seeing in our simulations. Furthermore, again, they estimated the growth rate for this instability, and if you plot the field strength as a function of time, we basically recreate the predicted growth rate. So again, this is really nice evidence that at least for the untwisted flux ropes, what we're seeing is the undular instability. Now, if we increase the twist, so now let's do a twist of, a higher, exceeding higher twist. We see at the photosphere basically that as you increase the twist, these undulations go away. So for a twist of 1 in the units of zeta that I showed earlier, you get these undulations, but there are less of them. They're less pronounced, they're more diffuse. You get more coherent polarities. As you increase the twist even more, these undulations basically completely go away. You get a really complicated active region, but you don't see these serpentine structures anymore. So if you plot the field lines, they look something like this. So you get these inverse U loops. Again, I'm not seeing any Slinkies, which Spiro is shocked by, I'm sure. But you do see a complicated structure, but nothing, concave up. And that kind of makes sense because that plasma can't be lifted. But we were wondering why, at low twist, it seems like you get these serpentine field lines, these undulations. At high twist, we don't see them anymore. And what we think is happening is that, so I have plotted here the magnetic flux slope as it's reaching the photosphere for different values of the twist. And the color scale is the local curvature. So as it's hitting at low twist, as it's hitting the photosphere, the flux is basically piling up until the magnetic pressure gradient is strong enough to lift it through the photosphere. At high twist, the curvature of the flux slope is so large that basically it's already concave down, and the plasma is just immediately able to drain, and it's able to emerge essentially bodily without forming these serpentine field lines. I should add that, for example, James has been doing these simulations for a long time, and his simulations really don't show so many of these undulations. And it turns out that the wavelength of this instability really matters. You need to have a large enough simulation box in order to capture some of these multiple undulations. Otherwise, you're not gonna see them. So if we look at, for example, the flux emergence rate in simulations, so here I have my simulations with different values of the twist. These diamonds are other simulations by James, by Matthias with convection, and these stars are the observed flux emergence rates. And so essentially what you see is that the simulations follow a completely different trend line than the observations. And so, unfortunately, I'm not going to have time to talk about other simulations where I do the inverse problem, where I keep twist constant and vary the rise speed. But, you might think, well, if you just change the rise speed, the flux emergence rate is going to depend on that. And I apologize, I've changed the color table on you all, but again, these are simulations with different rise speeds, and these are other simulations with convection and without convection. And here you have the observed flux emergence rates. And so it seems like still, we can't get the simulated flux emergence rates into agreement with the observations. And if there's one thing I learned from Spiro is that when the simulations and the observations disagree, the observers need to step their game up and explain what's happening. So, I'll leave that to the observers while I work on explaining it for the simulations. But there's clearly some fundamental process that we're not capturing here, that we can't explain the flux emergence rates that we're seeing in the observations. So I'll just end with saying that twist and rise speed, although I didn't get to that, they are key ingredients in determining the photospheric appearance of an emerging active region. At low twist, you get all these undulations, serpentine field lines, and a well-predicted scale length or wavelength for those features, a growth rate for these features. At a high twist, though, you get much more coherent active regions because the structure is so heavily curved that the thing is just able to emerge right away. And so an open question that I'm still working on is what determines the flux emergence rate and how we can bring it better into agreement with observations. So I'll stop there.
Very nice work, Kalman. So one of the difficulties with doing these emergence things is that the convection zone, radiative transfer is very important. So it's high beta, so you have to do the plasma accurately. But doing the plasma accurately is very difficult because you have to do all the radiative transfer at the same time as doing for the getting lower emergence rate.
Yeah, that's a great question. We have a HSR that we're working on to try to sort of improve a lot of these thermodynamics and physics that are in the model to try to see what effect that has. It's very possible that could. The other sort of idea that I had was that using Chi-Chi we can figure out maybe we're calculating the flux emergence rate incorrectly, and we're including flux from currents above that maybe isn't in the simulations. I'm not sure yet whether that will pan out, but yes, we're working on trying to figure that out. And Jim had a question.
So I'm trying to understand this undulation instability. The wavelength is perpendicular to the field, right? Not along the
The
field.
wavelength is, yeah, I guess I should have pointed out here that the axis from left to right here.
Yeah, so the field's going left to right.
Yeah.
And the wavelength of the undulation instability is going up and down. Is that correct or not?
There's a parallel mode and a perpendicular mode. And I admit that I don't have a good physical intuition for the perpendicular mode.
Right, that's the one that was confusing me. And the field lines, I would think, would kind of slip by each other and behave independently. So why is there a different wavelength?
I admit I don't have a good physical intuition. It could be somehow that how the plasma drains moves the field lines apart, but I'm not entirely sure. The papers that I've seen have not differentiated between the parallel and perpendicular modes. And so unfortunately I don't have a good answer for you.
Actually, I have a question.
Yeah.
What about the properties of the overlying magnetic field?
So here we don't have an overlying magnetic field, but we are working on including that. And I think the interaction between, let's say, the undulations and the overlying field should be really interesting. I mean, even within the undulations, we are seeing that the lobes are reconnecting, sort of the serpentine structure, the lobes are reconnecting with each other and forming these jets, which have been argued to be basically Ellerman bombs. So it would be interesting to see when we include an overlying field, how that interacts. Sorry, I wasn't talking.
Very interesting. I mean, I was just thinking that could also suppress the rise rate if,
Yeah, that's a fair point. Absolutely. Good point. Yeah.
solar flare ribbons and loops, and this is Joel Darlene.
Right, well, thank you, Judy. So that is indeed the title I submitted originally to SpiroFest, but I realized this is marvelous into the Spiro word cloud to go with a spectacular progress investigating reconnection outcomes. And I also wanted to acknowledge and thank Jim Klimchuk here for his nice work and organizing this meeting for entirely altruistic purposes. So anyway, so.
Apologies, could you turn on your handheld?
What's
It's
that?
currently off. A microphone that you're holding is off. If
Oh,
you
no.
can turn it on. Thank you.
Okay. You can hear me now? Great. Sorry, people online. Anyway, so you will see Spiro all over this talk. Anyway, so I want to start with a background on some of the work that I'll be talking about today. So, of course, the standard model, super highly effective at explaining many details of flare energy release, but some remain to be, fully figured out. Things like particle acceleration and burstiness, dynamics like quasi-periodic pulsations, and here, if I can point it anyway, you see a cat. Cat is wanting to bat the CME flux rope, and people who know Spiro knows his perpetual quote of, all the things, the impressive things his cat has done. So, anyway, back to the science. Plasmoids, which we've heard discussed already today, are leading candidates for explaining these features, particle acceleration and the burstiness. But our impasse, so to say, is that the reconnecting magnetic fields are very challenging to observe directly. So if we investigate flare ribbons, we can thereby indirectly diagnose reconnection and, for example, focusing on what fine structure might betray plasmoids in the corona. So that's what I'll be talking about in this presentation, to employ MHD modeling to bridge the theory and observations. So I'll give you a bit of a refresher. Many of you will be familiar with plasmoids, coherent magnetic structures generated by reconnection. It's already been mentioned how important they are for fast energy release, for particle acceleration, and for bursty energy release behavior. Again, it's been mentioned how plasmoid-like structures are observed in jets and CMEs, flares, a variety of places, but it's difficult to diagnose remotely in order to be able to get their properties. So what can we do with indirect observations? So here's a proposal that the plasmoids themselves can imprint their structure on ribbons. So ribbons, of course, these are the footpoints illuminated by energetic particle beams released by reconnection, at least so we think. And this can reveal information about the topology, energetics, reconnection rate, and so on. Much rich information is stored there. And so now high-resolution flare observations with IRIS, Big Bear Solar Observatory, reveal that there is quite a lot of fine structure in some of our observations of ribbons. And so a natural question is to ask if there would be a link to plasmoids. And so Peter Wyper, who's here, of course, and has done a lot of nice work on plasmoids, came up with an analytical magnetic field model where he moved around a plasmoid in a sort of analytic magnetic field, and so he found these nice sort of breaking wave structures in a proxy for ribbons. But so here I am to take a next step, building on that work by looking at it in a fully self-consistent MHD model. So here's the model, again, mentioning arms. This is idealized two-ribbon eruptive flare calculation, and you better believe there's breakout reconnection. This is a simulation I've been showing that involves guide field evolution and shear reduction. Here I'm focusing, despite the original title, primarily on the plasmoids. And I'm actually going to look at a lower resolution simulation today than some I've shown because, well, the high resolution ones are too complicated to analyze, frankly, to get nice connections. Well, maybe that's just an excuse, but you'll have to live with it. So anyway, many plasmoids do form in the current sheet, and we'll dig deeply into what that looks like. So many plasmoids do develop in the flare current sheet. So here's a couple of different views of the simulation. You have the flux rope in green. Let's see if I can manage to not mess this up. So you have an overhead view with a nice sort of current pattern here, this sort of sigmoid current pattern. This is after the flare's begun. And then if you look very close, you can see a little better some of the twist. It's always challenging to plot plasmoids in 3D. I'm not a Peter Wyper yet, but and these are all very interesting plasmoids. They're all precious. That's another soundbite from Spiro I'm sure many people will recognize. So there's some plasmoids. So Jim Klimchuk will be very happy about this one. So some of the plasmoids we see are very much three-dimensional, right? And of course, this is a 3D simulation, but you have here one of the particularly interesting cases where you have these two fluxes that are wrapped around each other, and you have these orange field lines that are totally, these sets of field lines are connected to the surface at both ends as if they would be flare loops. But you have wrapped around them this set of green field lines that go all the way around the flux rope and root near the flux rope foot point. So you have a lot of interesting structure and topology in these simulations. And this could not happen, of course, in 2D. And I'll also note that effectively there's 4 foot points of this structure, and so I'll be showing that in detail later. Okay, so we want to get back to the ribbons. Yeah, I know, it's going to keep going. I didn't hold back. Anyway, so what is our strategy for identifying ribbon proxies? So full forward modeling of ribbons is, not feasible at this point. Many, different partial ways of modeling are out there, but especially in arms with these high resolution simulations, it's just, you're not going to be able to do it right now. So key insight is that ribbons themselves, if we treat them as proxies for foot points of reconnection energy release sites, then we can look for the same thing in the simulations, and we're in both cases trying to understand something about the, reconnection. So as this movie on the right is playing, and as this, sort of, video on the left is playing, you can see that little frame of a Q map shows vertical current density, and Q maps can tell you some things about where the ribbons might be, but they involve gradients, they're coarse, they're noisy, they're not one-to-one to flare reconnection. So I've been trying to find a sort of more effective way to visualize the reconnection and identify ribbons. And so a key and kind of straightforward insight here, which Jiong was kind of alluding to later today, or earlier today, I should say, that field lines, if you trace them from the same spot over time as the ribbons spread across, the field line shorten. And so if you identify, look at the field line lengths and map the length of a field line to its point on the surface, these field line length maps can tell you a lot about what's going on. So I'll jump straight to a movie here where you can see this quantity is related to the length of the field line. And so let's see if I can make this play again. Hooray. Anyway, so you see here a lot of interesting structure here, which if you haven't looked at a bunch of these with me before is going to be not super obvious. So I have come up with a key for you a little bit here. So you have the ribbon motion, this outward pairwise motion of these shortened field lines away from the central polarity inversion line. You have these long field lines, which are essentially the mapping of the flux rope, and Jiong is smiling because she couldn't have given a better talk to set me up here. And then you have a lot of fine structure. You have interaction between the flux rope foot points and the sort of the flare loops, the flare ribbons, and between the flux rope foot points and the surrounding ambient field. So structure everywhere. And there's even a spine because, of course, there's breakout reconnection, and there's exciting fine structure there as well. So now that I've given you the key, hopefully this makes a little more sense. But yeah, I know there's a lot going on here. So thankfully, I'm going to zoom very far into just one of these fine structures. And so here we can look at a single plasmoid and its impact on the ribbon dynamics. So here on the left, I'm plotting the guide field, which wherever there's concentrations of the guide field, that's a reasonable proxy for where the plasmoids are, where there's compression. You take field lines, color-coded in rainbow colors, and map them down to the surface. And you'll see as this movie plays that there's a very nice correspondence between the plasmoid and the formation and then destruction of this sort of breaking wave structure, as Peter called it, on the surface. So, key thing here is you'll note that this one, the plasmoid is, I think I mislabeled this. This is supposed to be going down, but you can see the plasmoid forms and goes down, and what happens is that the structure fills in this case. So, yeah, this is what happens when you edit late at night. But anyway, so this other plasmoid, it's propagating upward, in fact. And so what you see here is that you see the formation of one of these structures, and now it kind of peels back and disappears. And so, just a kind of simple movie like this can show you how structures in the sort of, these contours between dark and light would basically be flare ribbons. So structures in that tells you something about creation, evolution, and destruction of plasmoids, and even which direction they're propagating. So here's a big old kind of confusogram movie, but at the top I show you the 4 sets of foot points for a given plasmoid. One of the ones I just showed, and so the ones in the bottom have to do with the flux rope foot points, and the ones in the middle are the 2 conjugate ribbons. And you can see here that the same plasmoid imprints in complex ways in each of these different regions. So tons of information there. So, okay. Spiro's favorite question. I can't avoid bringing up turbulence or complex structures. So, there's obviously more high-resolution versions of these simulations. Kind of the interesting but also hair-raising, hair-pulling out aspect of them is that you have many, many more plasmoids. So now it's not just tracing field lines from one plasmoid down to the surface, getting acute structure, but you have bits of flux coming in from other plasmoids and kind of turbulent dynamics. And the result is you get these sort of fractal-like plasmoid structures. So obviously this is more complicated, and so that requires more work to see what exactly you might be able to see in observations. But it's not so pessimistic because these still have that same sort of general breaking wave type of structure, even if the substructure, which probably wouldn't be able to see for a long time anyway, is on top of it. So, okay, so I've been showing a lot of these field line length maps, but observers, you might like to see something a little more concrete. So we can identify places where these field lines shorten, declare that to be flare reconnection, and then pretend they light up for 100 seconds, right? This is a very simple way of trying to mimic flare ribbons. And so, if you do this, zoom into one of these, this is one of the high resolution simulations, you get this kind of nice structure with these breaking waves. And, at least if you squint, it looks a lot like these iris observations. So I think that brings me to a close. Many of you might recognize a picture like this, famously decorating Spiro's office. But yes, thank you for your attention, and hit me with your questions. So.
Actually, you might consider joint observations of elongating loops. Think about it. So if you think of Jean's observations, she was looking at the dimmings, right? And those dimmings were related to the lengthening of loops. You have that in your simulations.
Yeah.
So you can actually do dimmings as well as the ribbons. Yeah.
I know,
You can
it's
do
almost
joint
too
observations
easy.
of elongating loops.
Yeah. I'm sure it'll be harder when you actually look at the data, but wow.
We need more acronyms.
Sorry. Well, this is tremendous, Joel. Something which is probably in here, but I somehow couldn't sort it out. So if you do as you've done, you start from a given foot point position and keep tracing the field line, and with the first reconnection, it shortens suddenly.
Yeah.
All right. And then presumably there are other reconnections which form the plasmoids. But then as the plasmoid gets absorbed into the arcade, from that same foot point, you should get a sudden lengthening of the field line. Now, it may just be a small lengthening if the plasmoid is a small plasmoid, but if it's a big plasmoid, you'll get quite a substantial lengthening. And this relates to what I've been kind of talking about for a while, that as plasmoids absorb into the arcade, you should see the flare ribbon expand in the backward direction temporarily. Do you see that temporary lengthening associated with the plasmoid reconnecting with the arcade?
So it's far more subtle than the main flare reconnection, because you go from all the way up, wrapping around the flux strobe to shorten down, right? There are definitely patterns I could see if I look closer. Could very well show this kind of thing. It's I'd have to look more carefully for it. We should finally sit down. I know we've been talking about this for a while, and I think the answer is in there, but so many things are in these simulations. So
I wonder if those breaking waves, maybe this plasmoid reconnection has a slip running kind of effect, which would lead to, I don't know. Sorry.
Oh.
The term word fractal, I mean self-similar behavior in the small, in the large scale connecting up, or maybe
so
differently?
I might basically be using it in a colloquial sense, in that if you zoom in further and zoom in further, there's layers and layers and layers, and so
imagine your simulations are infinitely accurate, then you can see
right, and that's a good point. But even with you can get chaos from a fairly simple set of equations. So, of course, you're interpolating, quite a bit to get these field lines. You get structure that's more fine, actually, than the resolution of the simulation, which doesn't mean that's precisely the structure of the simulation, but it does tell you that the kind of equations, give you chaos, give you fractal-like behavior, even if yes, no matter how good your field line tracer, you're not going to get it, 1-to-1.
Dana Long-Cope of MSU, and it's on chromospheric evaporation.
So
was
it changed my
technically
title.
on
Yeah.
chromospheric evaporation, but it's now on learning from FLIR light curves.
Yes. Yeah. So this is going to be a dramatic change from all this beautiful simulations and plots like this. This is going to be. This should work. No, I guess I point it here. Or I can put it up. The discussion of FLIR light curves and analytic modeling of FLIR light curves. And so basically, it's going to have the simplest light curves, the all sun goes light curves, two channels, low and high, from which you can get a proxy for temperature, shown here in green, and emission measure in red. And the light curves themselves, you see very rapid rises and then more gradual falls. And the emission measure tends to peak later than the temperature peaks. And there must be something, that must be telling us something. If you plot temperature versus emission measure, you get these nice phase diagrams, go around clockwise. And so you might think, who could help us understand this? And of course, we all know who could do this. Antiochus and Stark, 1978, really gave us sort of the guiding ideas that go into modeling FLIR loops. And the key insight here about the evaporation phase is that evaporation is just occurring as heat is conducting down to the feet, evaporating materials, which is just carrying the energy back up. So the energy isn't changing. You have a constant pressure. And then from that assumption, you can get an analytic expression for the evolution of temperature. And here it is plotted. So the evaporation phase. Well, 2 years later, he did by himself, started considering the next phase, the cooling by, I mean, you could think of the temperature decreasing as cooling, but in fact, there's no energy being lost. But in the radiative phase, the temperature is actually decreasing and the emission measure is too. And so he came up with some expressions for that. Then with Peter Cargill and John Mariska, sort of went through the two phases together, proposed this set of equations. Well, I mean, had been used before. And ultimately, that led to Jim Klimchuk and Spiros, but not Spiro, proposing the form that was going to solve these numerically, EBTEL. Okay. Oh, I'm sure he was. It's obvious that these all led together. And so I'll just talk you through the basic idea here is that during this evaporation phase, what Spiro had said is that the pressure is going to remain constant. So in this phase diagram between temperature and, in this case, density, it's going to go down this curve, logarithmic curve. So it's just a slope with, it's just a line with slope of -1. And then there's his original t to the minus 2/7 decrease in temperature, and then the increase in emission measure that has to follow it, or density. And then the next phase, and this is a bit of a wrinkle, but the next phase is something where you're going to have a uniform pressure. It's going to be changing, but because this is uniform, it is an RTV equilibrium, a Rosner, Tucker, and Viana equilibrium. And in those equilibria, the radiative losses and the conductive losses out of the corona match each other. More or less are equal. They're both losses. They're not balancing, right? But they basically, you can't have one go without the other. And that gives you a line along which this cooling must occur. And I labeled it radiative because that's what they started using. But in fact, it's equal parts conduction and radiation. And it goes down along that line. You get the curves that more or less that Spiro and Cargill and people showed. And you get that kind of curve there. And just to show you that they had it basically back in the 80s. If you do run EBTEL, you get, it's nicer rounded corners, but it basically follows the same triangular pattern there. And so you might say, well, the real light curves do that. And here are some of our favorite flares: the March 29th flare, the April 18th flare, the September 10th flare. And it's not great. I think if you use your imagination, you might convince yourself. But the key to getting models to agree with data is just to wait long enough for observations to come along that match your observation. Let me add, one explanation, and it's been provided by a lot of people: Harry Warren, Kathy Reeves, Zheng Chu, many people before that, is in fact a flare is not a single loop. It's just a collection of loops. And if you take that very same nice phase diagram and say, yeah, but I've got hundreds and hundreds of loops, but they're not all going off at the same time. Here they're all the same length, but they're probably not. You're going to get light curves that look a little more like this. But as I said, if you wait long enough, you will see an observation that looks a lot better. And here is the October 28th, 2021 flare. And the green is the GOES temperature and emission measure in a phase plot. The blue is a run of EBTEL. There's the evaporative phase. It doesn't match. It's sort of, you can see it's going down sort of along that line. The EBTEL, everything else too, the energy input is not instantaneous. It's occurring over a course of about 8 minutes. And so you don't actually reach a single temp pressure and stay there. Your pressure goes up a little bit. But the radiative cooling of the October 28th flare follows this curve impressively well. And so it looks like this really is the observation to prove Spiro's insights right, until you look at the time evolution. And then here, the blue and the red are the GOES emission measure and temperature. The green and the red. The blue is the EBTEL run, the same one you see the phase diagram for here. And the purple is the EBTEL emission measure. And it falls off quite a bit faster than reality. Remember, this is a log axis. And this is something we've known for a long time. The simple flare loop picture has things cooling much more rapidly than observations. Now you can explain that with multiple loops, but then you're going to get these phase diagrams that don't match this three-phase evolution. So this does seem to cool along the radiative curve, but it cools too quickly. And actually, there's more information. The gray shading here is not great. If you measure the temperature and emission measure, you can. I'll you get some insight into the volume, as I'll explain here. You can calculate the total thermal energy in the flare plasma. And if you know the cooling times, you can look at the amount of energy being lost, power going out of conduction in green, and radiation in blue, coronal radiation. And if you're cooling along that RTV curve, those two should match, and you can essentially adjust your parameters to give you a volume without actually having to look at the flare plasma. You'll just get a volume from matching these. But when you do that, you actually get a total power out, which is the purple here. It's the purple up here as well. And you know how quickly the thermal energy of the flare is going down. That's the red. And you're losing more energy to the losses. You are heating over this entire time, not just during the impulsive phase of the flare, not even during the evaporative phase of the flare, but during this long gradual phase, you are heating all the time. Thank you. And this is a kind of tail heating. Zhang Chu gave it that name in a paper in 2016. In this case, it's about 10 to the 27 ergs per second of tail heating that we see there. You can do a little bit more than Cargill, Mariska, and Antiochus. You can basically say, well, if there's a tail heating going on here, then I just have to solve this equation. That turns into this equation. There's one extra term. This is the one that will give you that Cargill cooling curve. If you add this extra one, you get an analytic solution. It does involve incomplete beta functions, but it's an analytic function. And here's the good news. If you look at the EPTEL run with this extra tail heating, it follows this blue curve here. The incomplete beta function gives you this black dashed. I actually offset it. It could be right on top of the EPTEL curve. And that's not too bad a picture of what's going on in the observations. So it's not doing so badly there. And you sort of recover the heat that you know is being added over this time. There's one last bit that gives us a very different confirmation of this picture, and that is using this method of tracking the individual foot points, in this case in 1600 angstroms, of each flare ribbon curve. And we were hearing a lot about the flare ribbons, and these are the light curves from the individual flare ribbons. Zhang Chu developed a method called the ultraviolet foot point calorimeter, and that gives us a way of turning these light curves into energy flux into the chromosphere from the flare. And you can actually see in each one of these, they do come in two parts. They have a prompt part, and then they have a long tail. And if you add up the long tail heating parts of these, you do get sort of a persistent about 10 to the 27 ergs per second in this flare tail that does give you that the light curves that you observe. So this very independent method is telling you the same thing, that this flare has an impulsive phase. This is actually where the hard X-rays are. An evaporative phase, and then this tail heating. If you look at the magnetic flux being reconnected, you get, by tracing the flare ribbons, you get this time rate of change of flux. And you can see by the time the tail heating is going on, there's really not much global reconnection going on. So whatever tail heating is, and I won't pretend I know, it doesn't seem to correspond to any motion of the ribbons. So I'll finish up there. The global light curves can tell us something about the physical mechanisms governing flare dynamics. And these are methods, analytical methods, that were pioneered by Spiro in the 70s. Many real flares don't exactly follow this, but we do have one example here that resembles the single flare loop model. It falls in line with the Antiochus schema, but it does require this additional tail heating. Thank you very much.
Thank you, Dana. Very nice talk. I just wanted to mention that for the late phase flare that I looked at in 2013, if you try to use the EPTEL to reconstruct the density and pressure, you also need like a very steady tail heating in order to explain the long delay of the late phase curve.
Oh, the late phase. Yeah, I have not looked into this late phase. I know about the late phase, but whether the tail heating is something that could be doing that.
Okay, I noticed that you plotted these GOES temperature emission measure.
Right.
Pressures. And at the beginning, there's this horizontal thing that wasn't anywhere near any curve. What do you think about that?
Over here? Yeah. I mean, I can't tell you what's going on there. Even EPTEL just is coming up, but yeah. No. That's sort of along the lines of what Hugh Hudson has been talking about in his early, that,
Dana, could the tail heating be just a steady stream of small plasmoids?
yeah, I mean, I don't see why not.
Okay.
We've looked, Will Ashfield in his PhD thesis looked at the possibility that it was alphane wave turbulence that's left over from the magnetic reconnection, but there's other options.
If you use UFC and make a map along the ribbon, is it the same value of energy you need for the tail heating, or is it super variable across?
It is somewhat variable. I mean, you can see in some of these, some loops have more, some foot points show more of the tail heating than others. So yeah, it is variable. Be very. I think I've made maps of how that looks. Yeah, I wish I remembered the result. I think it's sort of the very outer edges that have the sort of predominant tail heat, are dominated by tail heating. The very edge of this thing. In other words, I mean, again, you know, to give more evidence to Jim's hypothesis, these would be the part of the flare ribbon that's maybe connected to that overlying plasma sheet. Plasmoids or whatever are living in that plasma sheet. Right. Yeah. Yeah. No.
Let's thank Dana again. Next talk is on simulation. Oops, is that the right one? The wrong part of the day. Modeling shear in PRFLs, whatever they are, by Drake Osman and Martin.
Good try. My name is Drake Osman. I'm a second-year grad student at Montana State University. We've already heard from my thesis advisor, Jiong, and we just heard from Dana, my collaborators on this. So I'm going to be talking to you about modeling post-reconnection flare loops and magnetic shear involved with that. I'm also going to try to figure out this remote. It seems to be working so far. So just real quick, let's see if I can play this. So on the right side here, got a video of the flare with all these blue lines flickering over it. Those are some observed loops that we've picked up. So I'll let you just watch that for a second. And I'm going to be fitting field lines to this flare. So I'll talk about that fitting process. We have some benefits here that may allow us to do some powerful stuff with constraints. And then as a result, out of this, we end up finding magnetic shear decreases with time, which is something that's been observed for a while. Loop height increases with time, which is something you might have probably guessed during a flare. And finally, also that the linear force-free factor that I'm going to use decreases with time. So first off, what do I mean by magnetic shear? This is kind of how I'm going to quantify it with this shear angle. So you'll see that it's measured with the complement of the polarity inversion line. So if you actually have a shear angle of 0, that's going to be perpendicular to that polarity inversion line. And this has been done before. People have looked at magnetic shear. Particularly one example is Sue, and they've looked at kind of the centroids of flare ribbons, and then literally just connected those centroids with a line, like in this picture, and then measured that angle. There's been some other cases of similar work with different wavelengths, but similar ideas. And more recently, Jiong has actually used those same observed loops I showed you to get measurements on this. Spiro was also involved with that paper. So these are the actual observed loops. There's just a sample of some of the 304 angstrom. So this flare itself, though, was an M-class flare, M6. It did have a CME with it. It's from December, December 18th, 2014. And to get these observed loops that we're going to try to model, we've used Schwanden's oriented coronal curved loop tracing. And we have about 3,000 of them. So about twice as many in 304 as we do in the 171 angstroms. So those are the loops I'm going to try to fit. So here's kind of the range of parameters I'm going to search. I have before I do all this, I have 50 extrapolated linear force-free fields, and those are going to have a force-free parameter between about 0.13 and a potential field. It ends up being negative for this event, but you can kind of see the different kind of shapes of them. So those are field lines just traced from the foot points to give you an idea of these different linear force-free fields. We also have a height limit of 18 megameters. Nothing special about that. That's just when I stopped extrapolating. And it does happen to work pretty well for this. So how am I actually going to fit these field lines that we've observed? I'm going to start at the center of them. It seems the most reasonable to me. And then I have two problems. I don't know what alpha it should be, and I don't know what height it's going to be. I'm just going to brute force my way through it. So I will take one of those linear force-free fields, and I will search a range of heights up to about 18 megameters. And then I'll do that for all the linear force-free parameters. And similar work has been done with this, fitting force-free field lines to, or linear force-free field lines to non-linear force-free fields, especially in Malonenko and others. And also, some similar stuff was done in Warren. The big advantage we're going to have here in this work is we have some constraints that they didn't. Particularly, we know where the foot points kind of should be. We have the flare ribbons, so let's bring that up. So we have these ribbons that we've observed in the 1600 passband. The other constraint I've already mentioned, it's the top of my box for my magnetic fields. It's that 18 megameters. And it has to be longer than the observed loop in the aerospace. So I'll show you visually what that means in a second. But if you take a look at the ribbons, you can see they're very nice and kind of parallel, and they kind of spread out nicely. That's kind of what makes this event so nice to analyze. But I did just say in the aerospace, so I need to talk about what I mean by that. So this is how I actually measure how good of a fit we have. I bring them into this aerospace. So I rotate, and this is that same loop I had before, this loop, and I rotate it flat. Makes things nice. And then what I'm going to go and do, before I forget, that is that length limit I was talking about. If I draw a loop and it's not at least as long as the observed loop, it's probably not the observed loop, so we just kick it out immediately. It's considered invalid. So there's another nice constraint with the observed loop. It has to be at least as long as it. Here's an example of me showing you a bunch of different alphas for this particular line. It is the same line. These all hit foot points and we're under the height limit. So for how do I actually figure out the error, I'm just going to take these. So I've applied the same transformations to the modeled field line. I've shifted it to the origin and rotated it in the exact same way. And since they're nice and rotated and flat, I can just fit them with a nice spline and measure that error at, well, I do 50 points, but that's a bit much, so there's 10 points to look at. And I just take that absolute value of that difference. So I don't square it, I just take the absolute value. And then later on when I start comparing these to say which things are best, I will actually normalize to the arc length of the observed loop. So effectively it kind of becomes an average distance that the modeled loop is from the observed loop. If you're curious, this is the loop that won. And how does that look in the picture? It looks like that. So it looks pretty good to me. Here's an example of all of these loops I've found. It's not the most illuminating, but it's kind of fun to look at. And I do end up fitting about 95% of those observed loops I saw. So they still, even with the constraints, they're able to touch the foot points and stay under that height limit, and it works out quite nicely. As for the shear angle, so this closely mimics that work by Jiong earlier, because those are the observed loops that were used there. So these modeled loops, of course, result in a very similar shear angle. But we do see that decrease, which has been observed for a long time. Particularly in the beginning, it's quite a big drop-off. As for the errors, so here's just an example. I think I've grabbed the first quarter of my loops that I've looked at, and I've grabbed the last quarter just to show you kind of how much better that linear force-free factor being larger is at the beginning compared to the end with this normalized error. So once again, that's dividing by the arc length. So it's kind of effectively a distance. And those units would be pixels. And if we then take a look at how the alpha changes over time, one thing I should have mentioned before is there's like 14 points here. So I have a moving average here about every 3-4 minutes, which is about how long the loops tend to stay there when you watch the video. But we can see it decreases. Here's an example of, I think this is the about 3/4 of the way through, between half and 3/4 of the loops. Here's a height distribution I got for the ones that fit. You can see it's, most of them are about 10 megameters, but it's got a nice reasonable distribution, I think. And if we look at the height over time, they do tend to grow, as you might have guessed. So they go from about 6 to 12 megameters in the time I've looked at. But most importantly, if we actually take all of these loops that I've modeled and we take a look at just the foot points, and then we color code it by that linear force-free factor, we end up seeing a very similar pattern to the ribbons in that it spreads out. Let's see if I can get this. Oh, there we go. So you see a nice gradient along here, along that southern ribbon, as it goes in time, and the north ribbon, quite the angle, we'll also see that decrease in alpha over time. So it's not just going to a potential field, but over time it seems to be decreasing in alpha as these post-reconnection flare loops form. Quite interesting. So we did see that magnetic shear decreases, as you would expect. That's what the observed loops did. And they are forming at increasing heights, which you might imagine with that video of the flare loops forming as reconnection happens. But most interestingly, we see that alpha decreasing and making that nice kind of pattern over time that almost mimics that ribbon evolution. That's all I have.
So why do you think alpha is decreasing with time? Is it, some effect that has to do with the geometry of the field, or is it the transfer of some twist higher up?
I don't know if I'm the most qualified to answer that question, but I would imagine it has to do with the latter thing you said there, with twist being transferred maybe to that flux rope that's erupting.
Okay.
Yeah, you expect the alpha to decrease because what happens, the reconnection determines, or the location of the reconnection along the elongated field line prior to the going through the flare reconnection determines how much shear is left. So the lower lying field lines will lose less shear from their initial shear than the outer ones. But so that brings up the issue as to what is the initial value? Do you find that there is a kind of like a saturation as a maximum initial shear that you see in these flares, these flare loops?
At the time frame that I've looked at, that limit I've chosen, let's see, it's about the negative 0.13 inverse megameters. That ends up being, I almost dare. So I do think maybe if you looked earlier and you bump that alpha maximum up a little bit, or minimum, at least absolute maximum in magnitude, you might get a little bit more in the center there.
Hi. Have you considered using chromospheric coronal rain condensation to look for the loops closer in to get those values a bit closer?
I have not.
Okay, I have some nice data for that. We should talk.
Last but not least, talk of the session. Okay, inferring fundamental properties of the flare current sheet using flare ribbons. And this is obviously the ribbon session.
Oh.
So for Corchado Albelo.
Thank you so much. Yeah, thank you so much for everyone that stayed in. I know I'm the last talk person between you and dinner, so hopefully it'll be entertaining. Also, I think Joel did a great presentation as a kind of like introduction to what I'll be talking about. So there's going to be a lot of repetition for sure. I'm looking from the observation side, so hopefully we can provide you some things that you can look in your models and constrain. So maybe we get out of here. There we go. Great. So first thing that I wanted to show is the picture over there in the title slide was a very blown up image of a flare ribbon from this M3.7 flare that we observed in, there you go, there it's going, on November 4th on 2025. Now the interesting thing is, the reason why I blew it up as well, kind of like the main thing that we're interested in is this really high structured things that are forming on the flare ribbon fronts, and we want to understand kind of like what that can tell us of the flare reconnection itself. So the main science question is that, kind of like what are the properties of reconnection during the flare, and can we actually use flare ribbon observations to help constrain kind of like what might that physics be? And of course, kind of like one of the main insights that we have from a lot of analytical work and theoretical work from people in this very same room is that plasmoid dynamics might play a very important role in this. Now, of course, I'm not going to go through many details of the standard flare model, but the main thing being that, you know, as flare reconnection happens, you get the flare loops, and these are the anchors of these to the solar atmosphere are the flare ribbons, and you know, and just in, of course, it doesn't happen in a 2D plane, it happens in 3D, and in reality is that when it happens in 3D, it's not as nice as in this cartoon, it's very complicated, so understanding kind of like the flare observations, the flare ribbon observations can be difficult. Nonetheless, the flare ribbons provide us very unique information about, and a unique opportunity to diagnose or proxy at least, the reconnection flux because of this kind of like property that they are the anchors of the newly formed flare loops. So this talk, basically what we're going to be answering is reconnection happening in a kind of like bursty manner that can be described by oscillations? And basically, if these kind of like dynamics that we observe are in any way related to current sheet processes. The main thing that we're going to be using is we're going to be using a lot of data, SDO, IRIS, and Fermi and GOES. We use SDO to, again, build our flare ribbon maps and estimate a proxy of the reconnection flux. So that's how you do it. You just get a mass for it, and then you multiply it by the magnetic field from HMI, and you have your reconnection flux. Nonetheless, for the particle acceleration, we use as a proxy the hard X-ray emissions and also the soft X-ray rates through the Newport effect to compare with these. We use it through a very large range of channels to really understand kind of like what are the properties of, or the connection between particle acceleration through hard X-ray emission as a proxy, and reconnection fluxes and their evolution as a proxy with the flare ribbons. So the rest of the talk, I'll first show a couple of events, two of them, to really just showcase kind of like what is that we're doing in our analysis, and then I'll jump into some of the statistical results that we get from analyzing 73 flares. So the first thing, of course, I'll show a flare ribbon, over here evolving, and the main takeaway here is, of course, you have two of them, they evolve through time, and the main takeaway here is that although it might look like a very smooth transition, that is not what's actually happening. Same thing here with the reconnection flux that we can get out of this flare ribbon evolution. It might look kind of like smooth like at a first glance, but when we take the time derivative of it, we actually start to see some structure of how is the kind of like reconnection process actually happening. It's happening through these bursts that kind of look like oscillations. So again, going back to kind of like tying into some of the analytical work, we are very interested in seeing kind of like, well, flare reconnection is already happening through this bursty process, then, you know, again, it's like key point in kind of like a plasmoid dynamics happening in the flare reconnection sheet, so we might expect to see some fine structure, and we're not the first people to see it, but our idea is, are we seeing fine structure at the same time that we're seeing these kind of like bursts in the reconnection rate? And the answer is yes. Throughout the full evolution of this flare, we see time and time again different parts of the ribbon. Here I just highlighted a few where we see this really highly complicated structure forming on the flare ribbon fronts. And they're tied into kind of like this bursty process happening in the flare reconnection rates. Now, again, kind of like in trying to describe the oscillatory properties of these, well, we have to do a couple of things. The first thing is we're going to detrend kind of like the background, or I'll just kind of call it the background time series of each one of the observations that we have. So for the hard X-rays in the top, ghosts and reconnection rates. The second thing is we use the wavelet transform because it can be expected that these are not necessarily stationary wave modes that we're getting. It's probably non-stationary. So we use the wavelet transform as a way of identifying possible wave modes in our observations. And then, of course, we use the time average wave transform and Fourier transform to try to identify kind of like the more significant modes of oscillations in our data. And from this event, we see that the reconnection rate has, a period of about 2.5 minutes, and the hard X-rays have an oscillation period about 2 minutes. Now the Fourier transform over here, we're not going to continue using it in the future because it has a lot of issues in terms of processing it and identifying the key or most significant oscillations. The other thing that we care about is, as I mentioned at the beginning of the talk, is really understanding kind of like the statistical properties of these. So we have the 73 event catalog, and what we want to do is, like, again, do this same procedure of using the wavelet transform to study these oscillations and see how do they compare between the reconnection rates and the hard X-rays. And what we find is that in general, or in average, the reconnection rate oscillation periods tend to be a little bit higher than the hard X-ray ones and the soft X-ray rate ones. So they're about 1 minute of a difference. Now, the other important question is whether these oscillations are happening at the same time. So for that, we do some cross-correlation analysis, and we find that actually the reconnection rates, and again on average, happen before or precede the onset of the hard X-ray oscillation by about 24 seconds. Now, this is a tricky number because that is also the cadence of our instrument that we're using to analyze this data. So right now we're in this kind of like middle ground of understanding whether this is a systematic artifact and they're happening at the same time, or whether there's actually some physics behind this delay. That one is if it is a systematic. That's boring. Nonetheless, we reached the final slide, and the main takeaway here is that for these flares that I've shown, and there's 73 in total, we've seen these oscillations, and on average, again, the reconnection rate oscillation tends to be a little larger or bigger in period than the hard X-ray ones. Nonetheless, they're very close, so that might be due to, again, systematic things in terms of the cadences of the instruments not being the same thing. Now, in terms of the fine structure, again, this is the first key point in telling us that this might be related to some plasmoid dynamics, and there's been a lot of great work in terms of theory and numerical models in pushing that frontier. So again, I think main takeaway here is that our observations are providing maybe some evidence of this oscillatory motion, or sorry, oscillatory processes happening in the reconnection current sheet that at the end are kind of like probably dominated by plasmoid dynamics. There's definitely a lot of work to still be done in this frontier, but it's a step forward in terms of the observations. And if you want to learn more about it, you can, on the right is a keyboard code to our paper that you can read. It's on archive right now. It's been accepted to OBJ, so take a look if you find it interesting. And if not, you can ask me questions now. Thank you very much.
So Marcel, it's not so obvious how to tie the oscillations you see in the ribbon expansion with plasmoids because the plasmoids come down later in some sense, and they don't really move the ribbons forward. It's the first initial reconnection that starts to move the ribbons. You can see how the plasmoids, of course, could tie into the hard X-ray oscillations because they release the particles. When they come down, they release particles. If the plasmoids have some period, the particles will show some period. But the initial motion is a little puzzling. It's puzzling that the main reconnection would have this periodicity.
Yeah, so I think that is a very correct statement, and I think that's kind of like one of the things that we want to do is really get into some modeling as well in terms of like really trying to understand kind of like the timing between the plasmoid dynamics and what's actually happening to the flare ribbons, and maybe through proxies, the reconnection flux itself. One key point to address that question is the fact that the oscillations and the reconnection rates, they happen throughout like the full flare, whereas like in the hard X-rays, they're really confined specific times of the flare. So that's a key point of kind of like there's probably more to this picture. And in the paper, we talked a little bit about that as well.
Thank you. I'm interested. I'm still asking you a question both. But in your summary, you mentioned something about swirls. Did you see those in this presentation, or did you?
So I know sometimes in the communities, these words means, I guess, generically to refer to wave breaking patterns. I'm talking about this kind of like zigzag motion. When I talk about swirls, I talk about when basically like you have some form of something that might resemble a vortex or anything kind of like wrapping around itself.
Did you see those periodicities in this, or no?
Yeah, so I think like the main thing right now is that because there is not a straight definition in terms of observations, again, it's kind of, I guess, based on what it looks like, tracking kind of like when they happen and matching whether that corresponds to these oscillations over here is not straightforward. So right now we are looking into kind of like ways of automatically detecting this kind of like complex structure on the ribbon front. So that way we can actually track the evolution of when they show up and how they kind of like evolve over time and whether it's actually related to this kind of like burstiness or not. From our paper itself, this burstiness has to do with kind of like the larger scale evolution of the flare ribbon, because the data that we're using to derive our flare ribbons is the AIA one, which doesn't capture a lot of that fine structure.
And just one more, I guess. And if you look in like the AIA images of the erupting of flare, of the eruption and the evolution of the flare loops, do you see anything that might be shaking? Like maybe it was disturbed from the outside or something?
Yeah, they don't look as fascinating as the iris, which is why we show the iris ones. But definitely, yes, in terms of the flare ribbon front. And there's actually been, there's a paper by, I forget his first name, but Naus in I think 2021 or 2022, that described kind of like the evolution of the flare ribbon width. And it does match very well with kind of like this burstiness and the hard X-ray profiles. So even in, when we can't fully resolve all this structure, there is something in the flare ribbon front to be learned about kind of like what is happening in the flare current sheet and particle acceleration.
Excellent talk, Marcel. Thank you. Discussion on this, and I don't know if you'd like to, enlighten the audience. So for example, the ribbon area that's covering the magnetic field distribution here, it looks like a kind of a smooth, complex magnetic field configuration. And so one of the questions that I know we've discussed is that reconnection rate coming out of the structure of the magnetic field the ribbon's sweeping over, or is it something related to the flare sheet dynamics? And I think Joel's presentation lets us know that it's got something to do with the flare, because Joel's magnetic field distribution is smooth. So it has none of that same structure, yet they're seeing a lot of the same things we're looking at.
Costas Gontakakis. And I'm having a real hard time understanding the magnetic configuration, right? You have one polarity ribbon up at the top with that positive sunspot. Then the other negative polarity ribbon has this gigantic switchback structure. Do you have a magnetic model of that?
Does someone in the audience have a
Even
magnetic model?
what does it look like before the flare? What, the foot points are, and the two ribbons of opposite polarity are connected. And so what is the magnetic structure of that connection before the event?
Another weird thing about this particular flare, far apart, which is not normal for a standard.
Yep. I will point out that I think that's one of the main reasons why we took the approach of including 73 very different looking flares that share these kind of like dynamical properties, because I guess like from my perspective of this work, we did not do like the detailed modeling of what the magnetic field actually looks like, and I think that would be a fantastic project. But I think that the one thing that we wanted to get at is whether or not this is something important in flares in general, like this kind of like oscillatory reconnection dynamics, and whether or not it's and right now of course we kind of like selected 73 that do have them. A next step, the natural next step of this is checking kind of like over a very large database of flares, like how often does this happen where you do see like the oscillations? Is it a property of, as you said, kind of like complex active regions, or is it just something that's happening in any sort of flare? And I think I like to think that I've opened more questions than answered, and therefore I can at least continue doing stuff for my PhD. I am very much of that mentality right now.
Smart guy.
But yes, those are very fantastic questions that I don't have answers to.
That's the end of the session, I guess, right? So again, drinks, the bar is open at 5:45, and the meal will be available at 6:15. So I look forward to seeing everyone at the banquet, right over there.
What time tomorrow?
Well, it depends on you. I mean, Spiro's looking sharp as he always does. Erica asked me this question this morning. Did you? Yeah. So you said you had a cocktail dress you were going to probably put on. Yeah, so whatever you feel comfortable with, go for it. But do wear clothes.
We're here for the science.
Jim, by the way, this is already my favorite meeting ever because nobody went overtime. But good